Hello and welcome! You are watching part 3 of the trilogy that is the Pre-Calculus Spring Final Exam Review video box set. I don't know what you want to call it. But this is part 3 of 3. This is going to involve chapters 7, 10, and 12. Yes, we are skipping 8, 9, and 11 along the way. Part 1 had chapters 1 through 3. You can take a look at that. Part 2, chapters 4 through 6, all on trig. And part 3, chapter 7 is here. Solving systems of equations and inequalities with some partial fraction decomposition. I think there's one problem on that. Chapter 10 on conic sections, and along the way you'll see parametric and polar equations. And then chapter 12 starts the real calculus stuff on limits, derivatives, and even definite integrals. If you don't know this term, you've probably seen area of a shaded region underneath a curve or a line or something like that. So those are the 3 parts there. If you have trouble finding what it is you're looking for, please follow this down arrow here. If you're not in full screen, find the description section for which there will be timestamps for each individual problem that you are looking for. Now, I did add a couple word problems at the very end of chapter 7. They're problem numbers 10 and 11, so feel free to skip those if you don't have them, if you don't want to take a look at them. But those are the only word problems in this set, so I wanted to include a couple. They will be there. And finally, as you are going to have a calculator at some times, I have my handy-dandy calculator here available to you. I will use it only when necessary on my end, or if there's something that I feel has not been taught before with these kinds of problems. So without further ado, I will begin. And of course, remember, when I am doing these problems here, of course, I will be teaching them, but doing the process will be my intent for these problems for the sake of time. I know that these go a couple hours long in general anyway, but to save a little bit of time, I want to get you something to work with. Okay, chapter 7, here we go. Systems of equations and inequalities. Let's go to work. Number 1, solve the system graphically. Now, in terms of solving the system graphically, what is being asked of you is to graph these 2 equations here, and then to find the point of intersection, or points of intersection. Find the xy values that these guys intersect with. And if need be, I'd absolutely use a graphing calculator. For now, I'm going to go ahead and just use blue and green equations, try and draw them freehand just in case it's in a non-calculator portion, if you know what I mean. And then I'm going to see if I can get the points of intersection there. If I can't, I will go to the graphing calculator. So what I'm doing right now here with this blue equation on top is I'm going to get y by itself because I recognize that it's a parabola. Now that has probably more to do with conic sections in general, but this is kind of a standard form or a graphable form that I can use right here, where this is my y-intercept and this is my stretch factor. And oh, by the way, the y-intercept in this case is also my vertex. There is no horizontal shift of any kind here. So in graphing this blue equation here, first I'm going to start at 5/2, which is up 2.5. And I'm going to, every time instead of run 1, rise 1 squared, run 2, rise 2 squared, etc., I'm going to take those risen numbers and multiply them by -1/2, which means I'll go down, and I'll go down half the amount. Going over 1, down half of 1 squared is down 1/2. Over 2, down half of 2 squared is half of 4, which is 2. Over 3, down half of 3 squared, which is 4.5. So that's half, 1.5, 2.5, 3.5, 4.5. Down 4, over 4, down half of 16, which is 8. 1, 2, 3, 4, 5, 6, 7, 8. And I can probably even fit a 4th one, or a 5th one. Let me try in just a second. And reflecting across the axis of symmetry, that is x equals 0, allows me to do this as well. If I went over 5, I'd go down half of 25, which is 12. 12.5. So half, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Perfect. All right, so I got a whole bunch of points that I can work with here. And I can draw this curve, and it's not, I can't draw the curve very well, so I'm going to kind of rough it out like this. Computer screens and such, or drawing with computers, not really easy to do. So that part there, and then I have this part here. And there is a very nifty looking parabola accurate to its chord. It didn't take that long. It didn't use a table or anything else. Okay, the green equation right here, let's graph this one. This is going to be getting y by itself as well because it's a parabola. Let's subtract 3 squared and add 1. So negative y equals negative 3x squared plus 1. Multiply everything by -1. Y equals positive 3x squared minus 1. So same kind of thing. There's no shift in the horizontal sense, but there's a vertical shift downward. The y-intercept is the vertex at 0, -1. If I'm going to use a stretch factor of 3, go 1 away from the vertex, go up 1 squared times 3. That's right here. And you can already see that point of intersection. That's going to be one of them. Over 2, up 3 times 2 squared. So 3 times 4 is 12. Well, this is going to be 11 up here, so 12 is off the screen right there about. It's probably as far as I can get. Reflecting across the axis of symmetry here, I'll get that point there, which is an awesome another point of intersection. And right there. Now, if you use your graphing calculator, I'm just going to say it out loud because I'm not going to do it in this particular case. What you're going to do is graph these two equations, and you do have to get them in y equals format because that's what your graphing calculator has, y equals format. So get them in y equals format as well, and then find an appropriate window where you can see these two graphs intersect at your proper 2 points. And then to find those actual points of intersection, if you want to really get exact, which it looks like it's at 1, 2, and -1, 2, you would hit the second button, the calc button, where there's the trace thing right above, or excuse me, trace button where there's calc right above it. And then you would find, I think, option 5, which is intersect, and you can find those 2 points there. I believe I'll have to do that later, so we'll see. But right for now, I can freehand this one. 1, 2, and -1, 2 are my points of intersection for number 1. Number 2, solve the system by method of substitution. Okay, this time it's not being asked for you to graph. We, of course, could, but for the sake of time, I'm going to make sure that I find another means of doing that. So what I have right here is a quadratic and then a linear equation. And by substitution, of course, what they're referring to is get a variable isolated, substitute it in some sort of way. And look, I can substitute this many ways possible. If you want, I'll do 2 ways here. For one of them, I'll get x by itself and solve for y first. And then the other way, I'll get y by itself and solve for x first. Start with getting x by itself first. I'm going to get this x alone by adding y over. X equals y minus 2. Okay, x equals y minus 2. So I can substitute y minus 2 in place of x in the other equation right here, and then I can begin to solve for y. And as you can tell, this will lead to quadratic results. And that's quite all right. It's going to lead to them regardless. Just like last time we had 2 points of intersection. Looks like we may have the same thing here as well. We'll see. So y minus 2 is taking place of x in this top equation right here. I'm going to go ahead and solve for y as it's now by itself with no x's here. Y minus 2 quantity squared expands to y squared minus 4y plus 4. And then I'm going to distribute the 2 into there and continue to solve. Excuse me, this is a y squared. 2y squared minus 8y plus 8 minus y equals -2. As is a quadratic, it's probably best that I attempt to solve for this thing, getting everything on this side of the equation. So I'm going to add the 2 over, and I'm going to combine -8y and -9y. 2y squared minus 9y, add 2, you get plus 10 equals 0. And if all pans out, then this thing would be factorable. I'm going to play with that really quickly right now and see if it is. Positive product, negative sum. Both sets will be negative right here. Try 5 and 2. No, 2 and 5. Yes. So right here, y minus 2, 2y minus 5 is just the ticket that I need to solve for this thing. It is factorable. So to solve now, either 2y minus 5 equals 0. This is called zero product property. Or y minus 2 equals 0. In solving, you'll either get y equals 5 halves, which is 2.5, or y equals 2. Now these are 2 different y values for which these 2 equations intersect graphically. Okay, so what I'm going to do now is figure out what the x values are that associate with these y values, which means there are 2 different sets here. I'm going to substitute 2 for y in both in just one equation. It should work for both. But in one of the equations, probably the bottom one looks easier. Actually, this one right here, and I'll just solve for x, figure out what x is. So here when y is 5 halves, x looks like it's 5 halves minus 2. If you want to deal with fractions here, because you might have to at some point, 2 can be written as 4 over 2. So x is 1/2 in that case. Okay. The other way I can do it here, x is going to be y minus 2. That's 2 minus 2. So x is 0. So it looks like your 2 points of intersection for this problem here, solving by substitution, will be 0, 2, x, y, and then 1/2, 5 halves. And see, this This one, solving graphically without a graphing calculator, might not be our favorite thing to do here, might be less desired, but here it looks like we have exact answers. Let's confirm that we get those answers doing it a second way. So second way here, instead of getting x by itself, this time I'm going to get y by itself. And look, I can even do it in both equations here if I truly wanted to. And then I can use something that we call in Algebra 1 now, the equal values method. If I choose to get y by itself in both equations, I can subtract 2x squared and then multiply everything by -1, y would equal 2x squared plus 2. From here, I can either choose to substitute this into y for here, or here I can choose to isolate y as well by subtracting x over and then multiplying by -1, like that. And in the substitution realm, in the equal values method, this can take place of y over here. So now I can just straight up say that 2x squared plus 2 equals x plus 2. Boom. So now I have options for how I can solve this. Quadratically so, if I move everything to this side of the equation, set it equal to 0, subtract x, I'll get minus x here. Now subtract 2, that'll become 0, and on this side it's 0 as well. So 2x squared minus x equals 0. Make no bones about it, this should be easier to solve in this case than the previous one that you did, because the quadratic factoring has a common factor within. So I can factor the x out of both terms here, 2x minus 1 equals 0. And if this times this equals 0, either x equals 0 or 2x minus 1 equals 0. And if 2x minus 1 equals 0, then x would equal 1/2. So x is either 0 or 1/2. As you can see, we had those answers down here, 0 and 1/2. Now let's find the y values in either equation. Let's go ahead and use the bottom one here, y equals x plus 2. If y equals x plus 2, you can either say y equals 0 plus 2, which is 2, or y equals 1/2 plus 2, which kind of seems like we're going in circles from the previous problem, which is 1/2 plus 4/2, which is 5/2. So once again, your 2 points of intersection are 1/2 comma 5/2, and notice these have to associate with one another, and 0 comma 2. 1/2 comma 5/2 and 0 comma 2. Those are your two answers. I use substitution both times. Note, you cannot use elimination for a non-linear system in the way that you would really like to. I suppose you can do it to try and eliminate just the y's, but you could not do it to eliminate the x's in this case, and you'd have to use substitution on the x's thereafter. Number 3, solve the system by method of elimination and verifying the solution with the graphing utility. Because they're asking for this instruction, I will be doing that afterward. Okay, the elimination method entails that we are allowed to add down these sets provided that the right side equals the left side, and that if I'm going to combine like terms, I can actually make a variable go away. Now, if I added down the list immediately here, 6x plus 4x is 10x, y minus 3y is -2y, -2 plus 17 is 15. This does me no good, at least in essence here. I didn't eliminate any variables. So what I'm going to do is manipulate at least one of these two equations here. I'm actually going to manipulate the top equation so that one of my variables can eliminate, because I will have additive inverses on top and bottom equations here. If I eliminate, I can eliminate the y very easily if I multiply this top equation all by 3. That's done because what's going to happen here is this will be a positive 3y, and then negative 3y plus 3y will become 0. So I can ignore this equation if I so choose to right now. I might go back to it later, especially for the graphing calculator. And here's another equation that fits within our system. This is just a third equation that works within. Oh, whoops. This, yeah, -6. Good. Now I add down the list here. 4x plus 18x is 22x. -3y plus 3y is 0. 17 minus 6 is 11. 22x equals 11. X equals 11 over 22, which does reduce to 1/2. As far as fractions go, it's my favorite one. Very clean. I could even write the decimal 0.5. Now, if I want to solve for y based on this, like I said, I could revisit an old equation such as this one, because it did have y in it. It didn't have -3y. I'd prefer to use this. Take 1/2. Go ahead and substitute it in for x and solve for y. I mentioned in the previous problem that I could have just eliminated y without having to eliminate x and use substitution to then solve for x. That's what I'm doing here right now in solving for y. Subtract 3, get y equals -5. So my ordered pair here is 1/2, -5. An alternate way of solving this problem here, you can still eliminate x as you just did, or excuse me, eliminate y to solve for x here. What I could have also done was in full elimination, which I'll go ahead and show you, is I could have chosen to eliminate x next. Okay, if I eliminate x, then that is truly by elimination the whole way through, which I could have not done for problem number 2 to eliminate x. So what I'm going to do here is find a least common multiple for these values here that's going to pan out in such a way that I can eliminate my x values. Least common multiple of 6 and 4 is 12. If I multiply the top equation by 2 and the bottom equation by 3, I will get exactly what I'm looking for there. However, I would love for one of these to be negative. So how about I multiply the bottom by negative 3 here. So this is going to be negative 12x plus 3y. Excuse me, plus 9, 3 times 3y, plus 9y equals negative 51. And then, with the top equation here, I'm multiplying that by 2. This will be a positive 12x, exactly what I wanted, plus 2y equals negative 6. Go down the lists. We're going to get eliminate 11y equals negative 57. And something went wrong there. Let me, 2 times negative 2 is negative 4. I looked at the 3. So this should be negative 4 here. My apologies. 11y is negative, boom, 55. That looks a lot better. And y equals negative 5. Okay, so you get that negative 5 there. You still get the answer. Now confirm by graphing, or verify the solution with the graphing utility. So part of what I have to do with the graphing utility, if you recall from what I mentioned before, is you have to get y by itself in both equations. That's an absolute must with the graphing utility because they have y equals equations only, or at least with a TI graphing calculator. So get y by itself on top. That'll say y equals negative 6x minus 2. Get y by itself on bottom. So here's one of them. You get negative 3y equals negative 4x plus 17. And y equals 4/3 x minus 17/3. You can see why this bottom equation probably is not a fun one to solve with by graphing, given the slope and the y-intercept that we have there. Slope isn't bad because the rise over run fashion of it, but not using it against a y-intercept such as that one. Okay, so I'm going to do negative 6x plus 2 here, or minus 2, excuse me, minus 2, and then here I'll have 4/3 x minus 17/3. Now, as far as order of operations goes, it's actually not necessary for me to use parentheses here. It's important for you to note that this x is multiplying with the 4 before it's multiplying with the 3. The 3 is in the denominator, not the x there. So I have these two graphs. I'm going to go ahead and check it out with a standard window and see if they find the point of intersection for me. There it is right there. Let's actually find that using the calc button above trace. This is going to be second calc. Let's find the point of intersection there. Option 5. First curve is going to be this one. Second curve is going to be the other one. And guess, just make sure you're around that point there, not another one. 0.5, negative 5. Well, 0.5 is 1/2. Negative 5 is exactly that, negative 5. There we go. We're set with that problem there. Good solution. Moving on to the next, this is problem number 3. Problem number 4, the perimeter of a rectangle is 91 feet and the length is 8 feet more than twice the width. Find the dimensions of the rectangle. Okay, so there was a word problem here. I added a couple more later, but it's not bad to have some beforehand. So one thing you have to know about this problem is how rectangles work. Okay, some word problems fall under the assumption that you understand something about them. They are using the terms length and width, so I'll be doing the same thing here. It's called length, the vertical guys here, the width, the horizontal guys here. The perimeter is the addition of all 4 of these things right here. Perimeter of a rectangle is length plus width plus length plus width. That's 2 times the length plus 2 times the width there. That's perimeter of rectangle. This perimeter happens to be 91 feet long. So 2L plus 2W equals 91. By the way, I am breaking one of my rules here of defining variables first, but I'll do it just like that for now. And 91 is set there. The length is 8 feet more than twice the width. Okay, I know a lot of people get this stuff wrong at times. I'm going to start by writing L equals W, even if it's not true. But what I'm going to do is create an equation that compares L to W. That's the point. Does length equal width? No. Length is 8 more than not only the width, but twice the width. Now, what a lot of people tend to do is put L plus 8 over here, and let's use real numbers and try and make sense of that. If the length is 10, the width would be 18. Is 10 8 more than 18? No, it's 8 less than 18. If the length is 8 more than the width, I'm not talking about even, it's not twice the width, but if the length was even 8 more than the width, you'd have to add 8 to the width to get the length. So the 8 goes over here. You could put minus 8 on this side. But 8 feet more than twice the width. You have to double the width for it to even be 8 less than the length there. So here's your second setup here. 2L plus 2W equals 91, and L equals 2W plus 8. There is my system. Let's find out the dimensions of the rectangle. What is the length by width dimensions? So here it is, and this is set up for substitution more so than anything else because L equals this here. I'm going to substitute 2W plus 8 in for L in the top equation. And let's see what we can come up with here. Plus 2W equals 91. So 4W plus 16 plus 2W equals 91. 6W plus 16 equals 91. And solving the rest, 6W equals 75. So W equals 75 over 6. Probably not what I was looking for as far as a number. This can reduce. I can divide both by 3. 25 over 2. You could write 12.5. As far as length and width goes with this stuff, this number would probably look better to see as like it's 12.5 by whatever. I'm fine with that there. And I'm going to double check and make sure my stuff works out. No worries, because look, there could have been wrong math along the way, but I assume this to be okay so far. Now the length is 2W plus 8 here. So I'm going to go ahead and substitute in 12.5 in for W here. Which is going to 2 times 12.5 is 25. So 25 plus 8 is 33. Now they didn't give us units, I don't think. They didn't. So these are just units, not inches or whatever else. So far it looks like as far as length by width, it looks like this is a 33 by 12.5 dimensioned rectangle right there. I don't know if it's inches or what have you. They didn't ask us for area. They did ask us for dimensions. Let's confirm that that even works. 33, that would be length, which is not drawn to scale, obviously. 33 plus 33 is 66. 12.5 plus 12.5 is 25. 66 plus 25 is 91. Okay, so that one seems to pan out there. The second one is that the length is 8 feet more than twice the width. I think we've established that given using this equation here. It is 8 feet more than 25, which is twice 12.5. So there you go. There's a nice word problem. Now, I mentioned about defining variables. It's important to note what these variables represent, and these are the length of the length and the length of the width here. Problem 5, solve a system of linear equations. Okay. With this particular problem here, I've done substitution before. I'm just going to do elimination. If I do more than one, it's going to be a little hectic, and I don't want to work with fractions if I don't have to here. My end goal is to get a system of 4 here into a system of 3, and take that system of 3 and make it a system of 2. And obviously, as we do for systems of 2, we turn into a system of 1 to solve, and I'll trickle back up to find out all the other solutions. What I do see here is 2 equations that already have 3 variables in it, x, z, and w. What I'd love to do is take these other 2 equations here and, if at all possible, cancel out the y's here so that I can get another equation only full of x, z's, and w's. I think that's my best approach for this problem set right here. So I'm going to take equations 1 and 2, and I'm going to try and eliminate y. So in doing so, I'm going to take the bottom equation and multiply it by 3. Multiply it by 3 so I get positive 3y and negative 3y. So I have x plus 3y plus z equals 0. And then I have 15x minus 3y plus 3z plus 3w equals 0. Now I can add down these lists. X plus 15x is 16x. Z plus 3z is 4z. And then add the 3w, and this all equals 0. Okay, I have a third equation now with these other 2 equations here. I'll call these equations 3 and 4. And then this other equation 5. 3 and 4. and 5. I'm going to line those 3 up over here, 3, 4, and 5. And I might already look to say, okay, I want to eliminate something off the bat again. Okay. The last one it looks like I want to eliminate is x. No multiples of 3 can get you 16, and then it would get too large, like 48 or something huge like that. I'm going to shy away from those. Eliminating z actually wouldn't be too bad of an issue right here. However, because these w's are already lined up to eliminate immediately, I'm going to look to eliminate probably these two w's thereafter, the negative w and the positive 3w here. So let me just start with, instead of equation 5, let's start with 3 and 4 here. Let's add these ones down straight up, and I'll get 5x plus 4z equals 12 because the w's cancel. Now I'm going to take equations 4 and 5. See, equation 4 has a negative w, equation 5 has a positive 3w. If I take equation 4 and multiply it by 3, I'll get 9x plus 6z minus 3w equals 30. And then I can add it with this one here, 16x plus 4z plus 3w equals 0. And now the w's eliminate, and I'll have another equation with just x and z like this one here. So 25x plus 10z equals 30. And what's awesome about this equation here is all of these have multiples of 5 in it. I could divide everything by 5. Divide by 5 just to make them smaller, and I'll get 5x plus 2z equals 6. So now I have equations 6 and 7. At this point, I'm going to run out of how to do Roman numerals. 6 and 7 right here, and I'll go ahead and write this one underneath. 5x plus 4z equals 12. And as you can tell here, these guys are almost additive inverses, so I can eliminate x next pretty quickly if I make one of the equations all negative, 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 and I can add down the list again and go to work. 0 plus 2z equals 6, and z equals 3. Okay, what I do with this solution here is I start to trickle up. I take this solution here for z, I'm going to substitute it into one of these equations here to solve for x. Then I'll use those two, z and x, to solve for y, or excuse me, for w, then use all three of those to solve for y at the very top. So let's trickle up. Let's use this bottom equation here, equation 6, and solve for x. By the way, there's so many ways to solve this problem here. This is just one of them, giving you an example. And look, I haven't done this problem yet. This is my first time. So this is something that, you know, I saw this thing work out in a way that helped me here. 5x equals 0, so x equals 0. So z is 3, x is 0. Let's use those to solve for w. I'm going to take this equation. Oh, no, here, we can use it to solve for y right here as well. We can use both x and z perfectly. This equation, stay organized with your work if you can. 0 plus 3y plus z, which is 3, equals 0. 0 plus 3 is 3. Subtract 3. 3y is negative 3, so y is negative 1. And I have another equation, or systems of 3, that I can solve with w right here, like 2x plus 2z plus w equals 2. That's equation 3. 2x plus 2z, 2x plus 2z plus w equals 2, or negative 2? Positive 2. X was 0, z was 3, plus w equals 2. 0 gone. This is 6. Subtract 6. W is negative 4. So in terms of solving this system here, I got all my 4 values. I'm going to write it as an ordered quadruple, I guess you'd call it, in terms of w, x, y, and z, alphabetically so. Even if w is written last here, I'm going to maintain it in alphabetical order. This is going to be negative 4, comma 0, comma negative 1, comma 3. And I'm going to triple check or whatever that all of these are the correct values here by substituting into all of the equations. Negative 4, 0, negative 1, and 3. Negative 4, 0, negative 1, and 3. Okay, let's take a look. 0 minus 3 plus 3, negative 3 plus 3 is 0, equals 0. Check. 0 minus negative 1, that's positive 1, plus 3, which is 4, minus 0 equals 0. Check. 0, z is negative 1, minus, excuse me, it's 3, plus 6, minus 4 is 2. Check. 0 plus 6 minus negative 4. 6 plus 4 is 10. Check. So here's your ordered quadruple right there. Number 6, find the position equation S equals 1/2 AT squared plus V naught plus S naught, or V sub 0, S sub 0, for an object at the given heights moving vertically at the specified times. To verify your result, use a graphing utility to plot the points and graph the parabola. Okay, so this problem looks a little more confusing than we really need it to be. What we have are a bunch of coefficients here, and S and T will be your variables. S is regarding position, T is regarding time, and these things can vary. We want to find the constants A, V naught, and S naught right here. These will be like your stretch factor, you know, your times 1/2 is going to be your quadratic coefficient. This guy here looks like, you know, I think there should be a T here, V naught times T. I think there's an issue with this problem here. I really think a T is going to be there. This should be your linear coefficient, and this should be your constant right here. And I'm going to double, triple, quadruple check. Well, you know, I think this is supposed to be here. I'm just going to go ahead and write that. Otherwise, these two would combine, and it wouldn't be much of a of what I'm looking for, knowing my physics here. So what we know is that at t equals 1 second, S equals 88 feet, 2, 112, 304. What we can do is we can create a system of equations with this by substituting these values into here, and then we can solve for what S and T would, or excuse me, what A, V naught, and S naught would have to be based on that info. So for this top one right here, I'm going to color code them in blue. I'm going to do S is 88, and I'm actually going to write that at the end. I like writing my constants at the end there. And that'll be 1/2 times A times T squared plus V naught times T plus S naught there equals 88. And then in green, here I have 1/2 times A 2 squared plus V naught times 2 plus S naught. This all equals 112. 112. Okay, finally, substitute 3 and 104, same thing. Let's use purple. Whoops. Let's get 1/2 times A times T, 3 squared plus V naught times 3 plus S naught equals S naught, it's not 104. Okay. And as you can see, it looks like at t equals 3, it went lower. It went down, right? Went up and down, parabola. So, okay, in terms of condensing this a little bit better, simplifying this a little better here, 1 squared is 1 times 1/2 is 1/2. So I have 1/2 A plus 1 times V naught, 1 times V naught, boom, plus S naught equals 88. Here, 2 squared is 4. 1/2 of 4 is 2. 2A plus 2 times V naught plus S naught equals 112. And finally, 3 squared is 9. 9 halves is going to go here. 9 halves times A plus 3 times V naught plus S naught equals 104. One other thing that will make me a little more comfortable with these problems here is if the fractions are gone. I'm not particularly enthused to be using these things not as fractions. This is equations 1, 2, and 3. Equations 1 and 3 have fractions within. I'm going to go ahead and multiply these ones by 2. Times 2 and times 2. I'm going to rewrite these one last time before I start solving for these variables here. So multiplying by 2, I'll get A plus 2 V naught plus 2 S naught equals 176 for equation 1. Equation 2 is still 2A plus 2 V naught plus S naught equals 112. And then multiply the bottom one by 2. I'm going to get 9A plus 6 V naught plus 2 S naught equals 208. All right. So the end goal in this thing is to solve for all three of these variables here. It doesn't really matter which one you solve for first here. I probably don't want to solve for a for the same reason that 2a doesn't go into 9 very easily here. Looks like if we multiply both these equations by -3, we could get rid of the v naught here as well. This would be also easy to eliminate too. Probably going to go with this one here, smaller numbers to work with in general. If I take the top equation, equation number 1, and multiply it by -1 here, then I can line it up with the bottom equation number 3, and I can eliminate the s naughts right here. So I'll have -a minus 2v naught minus 2s naught, and this will equal -176. Everything turned negative with these two equations here. These two equations here, I'm going to add down the lists, and I'll get 9a minus a is 8a, 6v naught minus 2v naught is 4v naught. These guys cancel right here, and this will equal 32. These can all divide by 4 and reduce if I need to do that as well. So that's also 2a plus v naught equals 8. I have a nice simplified equation there with just two variables. I'm going to go ahead and eliminate the s naughts from another set of two equations to make the rest work. So let's take these two equations right here, equations 1 and 2. If I multiply this one here by -2, I'm going to eliminate the s naughts right there, and I'll have these two equations, a plus 2v naught plus 2 s naught equals 176, and then I have -2. So -4a plus, minus 4v naught minus 2 s naught equals -224. Adding down the lists, I'll get -3a minus 2v naught equals, let's see, that would give you 6, that's 48, -48. Okay, so getting these ones written right next to each other, and you might say, hey, let's make those positive. Well, I might want to eliminate the v naughts there. So let's see, keep this negative. -3a minus 2v naught equals -48. Okay. System of 2, let's go ahead and solve this one. Let's take that top equation right there and let's double it. And we'll get 4a plus 2v naught equals 16. Let's go ahead and start solving here. Eliminate a is apparently going to be -32. Now, that number looks a little correct on my end. Because something I know about these kinds of equations with physics is gravity gets affected as far as, I think these meters per second or feet or like whatever. As far as the -32 goes, half of -32 is -16. That's what you're going to see in a lot of physics problems. So I trust the a value is correct just based on my own experiences within physics, the physics world of calculus and all that such. All right, let's solve for v naught, the velocity component regarding this stuff right here, the initial velocity component, I should say. Substitute -32 in for a in one of these equations. How about this one right here, this guy? So I'll get 2 times -32 plus v naught. That equals 8. So -64 plus v naught equals 8. Add 64, v naught equals 72. Yeah. Let's use both of these to solve for for s naught. Where's an equation with a simple s naught? How about this one right here? 2a plus 2v naught plus s naught equals 112. 2a plus 2v naught plus s naught. This is initial position, by the way, equals, I think, 112. 112. That's -64 plus 144 plus s naught equals 112. That's 80 plus s naught equals 112. So s naught equals 32. Initial position right there. So if I have those three in our equations, the three constants there, I can rewrite this thing here. And yeah, a t is supposed to be here. I'm fully trusting that a t is supposed to be there, not this plus. This will be 1/2. So s equals 1/2 times -32 t squared plus v naught, so it's plus 72 times t plus 32, which is s equals negative 16 t squared plus 72t plus 32. To find the position, and I'm actually more familiar with seeing this as s of t, not that that matters one way or the other. It's my own comfortability. To find the position of this thing, what is this thing? To find the position of this object moving vertically, I can substitute a value for t, and then I can get what the s actual position is. Now, they said to use a graphing calculator to verify that these points exist on this thing here. So I'm going to go ahead and do that. I'm going to substitute, I'm going to use y for s and x for t, obviously, here. So negative 16, let's go t squared plus 72t, or 72x, plus 32. And let's fit this in a certain window that we know would probably apply here. For starters, we know we have to go up at least to 112 for y here. So I'm going to start at 0 here. I don't care what's before that. Yeah, that's fine going out to 10 for now. We'll probably shrink it later. Y, I'll start at 0. Look, we're going to start at 32. I'm going to go at least to, how about 125 here? Let's see if I have enough room to see this on the graphing calculator. Boom. There's the arc of the projectile, or whatever, the motion of the projectile. And it hits some top part, and it goes back down and hits rock bottom, almost at 5, maybe exactly at 5. But let's go to the table. Let's go to the table and see if these points exist here. So at t equals 1, 2, and 3. I'll start at 0, increment by 1 each, and let's see what we got. When t is 0, we're at 32. That makes sense for this problem here. 1 is 88, 2 is 112, 3 is 104. And 464, 5 is negative 8. So it looks like it would hit the ground or whatever that is prior to 5 seconds. But it does hit those points right there, and that's what we were looking for. We do have an equation that models it. My apologies for not having that t right there. Should be there for that kind of problem. Otherwise, these things would kind of just combine straight up, and it's probably not what we're looking to do for this particular kind of problem, just regarding the physics that I'm aware of there. Okay, number 7, find the partial fraction decomposition of 5x squared plus 12x plus 10 over x plus 1 quantity cubed. Partial fraction decomposition is referring to this thing might be a culmination here. This thing might be a culmination of possibly 3 split fractions. And I'm saying 3 because of kind of how I can split this set of factorization up. 3 fractions that didn't have common denominators to begin with. Now, what you'd normally probably look to do is factor a quadratic down below, see what kinds of multiples of numbers there are, and uniquely split those up. And what we do is figure out what numerators go on top, what string of numerators or constant values here. So what I'm going to do to make these things non-common denominators is I'm going to go ahead and split it up so that I have one of them just be x plus 1, because look, all your factors are x plus 1. I'll make one of them just x plus 1, like x plus 1 to the first power, and my on top numerator, unknown, will be a constant value a. Underneath this one, let's do x plus 1 quantity squared to say these are unlike. And for a reason to make it cubed in the first place, let's go ahead and make one x plus 1 quantity cubed. Therefore, none of these denominators are the same. Okay, none of these denominators are the same, and what we're looking to do here is find out what these numerators were prior to making this into one large common denominator like this. So 5x squared plus 12x plus 10, which, by the way, I don't think is factorable. Even if it was, we're not looking to factor the top. You'll see why in a moment. Over x plus 1 quantity cubed equals all this. In order to figure out what this a, b, and c are, this is going to be yet again another system. I'll multiply both sides by x plus 1 quantity cubed. X plus 1 quantity cubed here, and then over here multiply by x plus 1 quantity cubed. Well, if you multiply this first one by x plus 1 quantity cubed, there will be one multiple that will cancel on top and bottom. All that you'll be left with the a is x plus 1 quantity squared. By the way, up here, these canceled. 5x squared plus 12x plus 10. When I multiply this one with b right here, x2 degrees of x plus 1 here, 2 factors will cancel. You'll be left with just one linear factor of x plus 1 there. And finally, with c, when you do it, it looks like they cancel out as well, so you're just left with plus c. My end goal here is to express this number 5 in terms of the letters a, b, and c. 12 in terms of the letters A, B, and C, and 10 in terms of the letters A, B, and C. So I'm going to leave this left side unaffected here. On the right side, what I'm going to do is expand all these things and even distribute the A and B and C into these so that I can find common factors with x, find an x squared common factor, an x common factor, and a constant common factor. So A times this right here, this will expand to x squared plus 2x plus 1. B, it looks like I can already distribute this. This will be bx plus b. And then this is plus c. So this one I got to distribute the a here. Okay, this will be ax squared plus 2 times a times x plus a. Then plus bx plus b plus c. I'm going to do a little bit of reordering here, and I'm going to color code this time. 5x squared. I'm going to group all my x squareds together. It looks like there's only one x squared term right here, so I'll leave that be. Ax squared. Then I have plus 12x. The linear terms, I'm going to make purple here. 12x, so there's a 2ax and there's a bx. I'm going to group those together. And then plus c, let's go ahead and make red. The constant values, looks like I have a, b, and c. Okay. One more look with these right here. 5x squared. Basically, if this is 5 times x squared right here, and this is a times x squared, then we know that a is equal to 5. A and 5, I'm going to write this a little larger. A is equal to 5. A and 5 must be the same thing. 5x squared and ax squared. That's the only thing that's expressing x squared there. But the linear factorization here, 12x, is set with, see this common factor of x here? X is multiplying with 2a and b. That must mean that as 12 multiplies with x and 2a plus b multiplies with x, then 2a plus b must be the same thing that 12 is. 2a plus b must be equal to 12. Finally, we have a plus b plus c here. This entire quantity must be everything that, why did I put plus c here? That should say 10. A plus b plus c must represent 10, the last thing right there, so I can write that out. A plus b plus c equals 10. So voila, I have a system of 3 right here, and I can solve for a, b, and c and determine what this original decomposed set of fraction values were going to be based on it. Well, I already know that a is 5, so I'm going to go and trickle down here. 2 times 5 plus b is 12. 10 plus b is 12, so b is 2. A is 5, b is 2, and then 5 plus 2 plus c equals 10. 7 plus c equals 10, so c equals 3. So these letters here represent the numerators that go in that decomposed fraction that I put here before, decomposed set of fractions I put in here before, and that'll be the final solution set. So let me write it one more time down below. 5x squared plus 12x plus 10 over x plus 1 quantity cubed. 5x squared plus 12x plus 10 over x plus 1 quantity cubed is equal to this decomposed set here. A is 5. So this will be 5 over x plus 1 plus 2 over x plus 1 quantity squared, that was b, plus 3 over x plus 1 quantity cubed. Now normally, ordinarily we would do problems where you have the right side and they ask you to write it as one fraction on the left side here. This will have use in calculus as far as decomposition goes. And this would be a set that if we did find common denominator, we would end up getting this result. Multiply this top and bottom by something, and this top and bottom by something to match this common denominator. And there you go. Number 8, using a graphing utility, graph y is greater than e to the x. Certainly, I'm going to go ahead and do what they ask here. So using the graphing utility here, I'm going to do y is greater than e to the x. Now, one thing here is that we can kind of do a broken line if we did a dotted mode right here. Where is it? If we did dotted mode right here, Sometimes your calculator will kind of help you with that. But what I want to do is really work on the greater than idea here. I'll know to draw a broken line myself. If I want to do greater than, I'm going to be representing it with this guy here, the above the y kind of thing. So it's the shading in the top right corner there. And I just hit the enter button to the left here until I found that. Y is greater than e to the x, e to the x right here. If I go in graphing mode and I have a strange window for now, I'm going to go to a standard window here, negative 9.4 to 9.4, negative 6.2 to 6.2. That squares off my window set, not even negative 10 to 10. Then I have this graph right here, and it looks kind of strange there, but you can see that it starts to go up. Now, we're going to go ahead and draw this graph as well, and, you know, I'll just do the best I can here with what's given. I know that E is around 2.7, so this guy will go right here, and, excuse me, 1 goes here. This is e to the 0 power. I already messed that up. 1 goes here. E to the first power is around 2.7 there. E squared, I think it's around 7.4 or something like that. 3, 4, 5, 6, 7.4, maybe something like that. But anyway, so it just says use the graphing utility and draw. Obviously, it's more about drawing a sketch, not to scale here. I'm going to draw a dotted curve to represent the fact that this, the curve is not a part of your solution set. It is a boundary curve. It is a threshold to represent that which would be greater than or less than. So as far as this thing, it is greater than when compared to y, so I will be shading above this curve at every set of points here. So shading above would go here, just like the graphing calculator also shows. Thank you, graphing calculator. You helped me out graphing this guy here. And we are set. Number 9, use a graphing utility to graph the system of equalities. So we have x plus y is greater than or equal to 2. Y is less than or equal to x, and y is greater than 0. Now, once again, you know, this is something that, look, I could do this by hand, you could do this by hand, but I'm just going off what this thing says. Use the graphing utility. I'm going to go ahead and you know, work with their request there. So let's go ahead and do that. All right, let's get the calculator out of the way for just, well, actually, I can leave it there. So x plus y is greater than or equal to 2 here. Let's get y by itself. Remember, the end goal for this stuff is to get these into y equals equations so we can use it for our calculator. Negative x plus 2 there. And then we have y is less than or equal to x. And then y is greater than 0. Okay, so here we go. Graphing calculator. Now, again, the calculator cannot differentiate shaded from solid, at least nothing that I know of. You know, I'm sure there's a way to do it. I mean, it's a graphing calculator, for Pete's sake. But shading above for greater than or equal to. For less than or equal to, I'm going to shade below. So I'm going to look at this one down here, press enter a couple times, and shade below, and that's going to be x. And then I'll compare it to 0 finally here, and it's going to be greater than that one. And hopefully, just hopefully, I can figure out the confusion that this graph might have with the shading and see if I can find my final solution set. Okay, good. All right, so that's not too bad here. So the final shaded region will be this dark area right here, the one that actually has all three things intersect. And I'm going to use that to help me draw this graph here. In order to do that, let's color code these actually specifically. Let's get y. Let's get y is less than or equal to x, a different color. Let's get y is greater than or equal to 0, a different color here. I'll make this green, make this red. And let's go ahead and graph these three things. And of course, you'd have to know what order these were in and everything else, but at least this thing gave you a good start. I'm going to do y is greater than 0 first. It's going to be a dotted line. It's going to be going across the x-axis like this. And I'll be shading above, above, above. So let's go ahead, shade above, and make it thick. And here we go. That's where we're shading here according to the graph. Okay. Next one I'm going to do in green is going to be y is less than or equal to x. It's the one that's going diagonally upward to the right, like this one right here, less than or equal to shading underneath. Y is less than or equal to x, as also equal to, it will be a solid line, and it's going right through the origin here, so it's looking a little bit like this right here, and then I shade below. I shade below and I shade in green here. So green, below, we're looking at something like this here. Okay, and you can see that point of intersection kind of fading in right there. And I'm using the graphing utility kind of just to confirm my answer, but we still have to draw it. And if we have to draw this one to scale, by all means, we have to know what it is we're looking at. So understand when you're shading above and below, and we have to know solid versus broken lines. The last one here that stayed in blue, and it's greater than or equal to, so it's solid. It crosses at 2, and it has a slope of -1. You can see going down and to the right there. And then it also, we shade above. So y is greater than or equal to -x plus 2 here. We're going to shade this one in blue. And it's going to look like this one right here. And your final set, the actual final set, is the one that's in this. I'll go ahead and letter them off. But it's the one that's on the far right that's above the x-axis right here that I'm coloring kind of right now. Okay, so that's going to be the final solution set because that contains all 3 of these things together. And that means anything inside that shaded region, including the ones on the solid boundary lines, would be solution sets to this system of inequalities here. So if I label these things regions A, B, C, D, and E, E and F, region D, and G. Region D is the one that it has all of them together there. Okay, all of them together there. That's what we're looking at right there. That's number 9. Okay, here's some bonus problems here, numbers 10, and there will be an 11 as well. And I know there are a lot of words. I'm just going to break this thing down and see, because this one I kind of have to use a calculator with, I think. So we'll see how we do. After prom, you and your limousine party group decide to drive through In-N-Out Burger. Awesome. To make the order simple, everybody agrees to purchase only purchase double burgers and or fries. Double is two meat and 2 slices of cheese. In the order, a total of 24 doubles and 12 orders of fries were placed. So a combination of all your friends. All right, that'll be 24 doubles and 12 orders of fries. The total cost with tax is $111.12. And to kind of make things easy to let the drive-through thing go, you say, hey, don't worry, I'll pay for it. You opt to pay for the entire meal up front. Just you guys all pay me back while we're eating, after you eat, later, whatever. With the receipt, everyone will pay you back exact change based on their orders. Unfortunately, you leave the receipt with your trash bags and lose it. It falls in the trash, throw it away. Uh-oh, how much do we owe you? You recall the last time you bought one double and 1 order of fries. The overall cost was $5.50 with tax. And you decide that based on this information that you know of this number, so you remember this number and these numbers here, and you know this set here, you decide you can recalculate the costs on your own so everyone can pay you back with exact change. Determine the cost of just 1 double and cost of 1 order of fries, just separately, not the total $5.50. Okay, so what we have here, I'm going to go ahead and do that define variables idea so we know exactly what it is that we're looking for as we do this. I'm going to set 2 variables here. Let's do B for burgers. Let's let B equal the cost, the thing we don't know, cost of 1 double. I'll just put DD. This unit is going to be in dollars. I want my final unit to be in dollars. Decimals would represent cents if we have any. F is going to represent cost of 1 order of fries. Cost of 1 order of fries, also in dollars. Okay, so these are costs. This is not amount of, like not number of. We already know those sets based on these. We have to figure out the costs. We're going to create 2 equations. One based on the top info, one based on the bottom info here. Let's do the bottom one first. If I take the cost of 1 double with the cost of 1 order of fries, that total is going to be $5.50 or $5.5, which is $5.50. 24 doubles would take the cost of 1 double and multiplying it by 24. That's going to be the cost of all my double burgers, plus the 12 orders of fries. That'll be 1 order of fries, or the cost of 1 order of fries times 12 fries. That's going to total $111.12. So here's my system. We're going to solve for this system here. And this is part A. We're going to use the answer for A to get part B, which is on the next slide. So what I'm going to do here is use elimination. I'm going to multiply this by -12. I'm going to eliminate F and solve for B first. We'll get -12 times B minus 12 times F. This equals, and I have the calculator to work with here, 5.5 times 12. I should know it because you're doing 12 times 5, which is 60. Half of 12 then is 6, and multiply that, and you'll get 30. So 6 plus 30 should be 90. So 12 times 5.5 is I did that wrong. I said something wrong. I don't know why I multiplied by 12. 66. See, don't say something that you don't know. All right. 12 times 5.5. Duh. I thought of something else. Ignore me. 66. Negative 66. Make a fool out of yourself, Mr. Robinson. Perfect. That's why you're leaving it on here. It's why you're not editing it out. People make mistakes. 12b equals, I better be able to do this, 1112 minus 66 here. That'll be $45.12. Okay, so you divide by 12 here. I will do that with the calculator. Whoops. In the calculator here, $45.12 divided by 12 will give us $3.76. 3.76 will be what B is equal to here. So here we go. B equals 3.76. That is the cost, apparently, of one double burger. Now I can use that to solve for F, the cost of one order of fries there. We have B plus F, I see the one on top. B plus F equals 550. So 3.76 plus F is 550. So subtract 376, that'll be $1.74, 1.74 right there. So the cost of one double burger, of one double burger is $3.76. And the cost of one order of fries is $1.74. So now your buddies can pay you back. You say, hey, you owe me this much. And by the way, this is with tax, all that stuff. So, hey, you can pay me back this much, whatever it is, based on how much they knew they ordered. They don't know how much it cost. They know what they ordered, though. Okay, so 376 and 174. Keep that in mind for this next part. Part B, same description. That same night, Mr. Robinson also went to In-N-Out Burger and ordered 2 doubles and 1 order of cheese fries. Now, for cheese fries, this is one of my complaints about In-N-Out Burger. They overcharge me for cheese fries, dude. $2 extra for the cheese? I don't think so. I guess the melted cheese, the fact they have to use the oven. I don't know what it is. How much was Mr. Robinson charged for his order in total? So basically what happened is I ordered 2 doubles here. We know that the cost of one of them is $3.76. We know the cost of one order of fries is $1.74 here. So I'm going to take 2 doubles, multiply 2 by $3.76. Then I'm going to do the order of fries. And then there's a $2 surcharge because of melting cheese onto my fries there. I'm going to calculate what that is. That's going to be my total order amount. So 2 times 3.76 there, 2 doubles would be 752. Then I have the plus 174 plus 2 there. That'll be plus 374. And that'll equal $11.26. $11.26. Mr. Robinson, Mr. R was charged $11.26. There's no tax on the surcharge there. They're just going to add $2 to the thing. I hope all that makes sense, that charge is kind of already configured into this. You're good. That's it. Number 11, the last word problem here. The sum of the digits of a 2-digit number is 18. Is 18 less than the number itself. When the digits are reversed, the new number is increased by 27 when compared to the original number. What was the original 2-digit number? Okay, first of all, I'm going to get rid of the calculator. Right now, it's not going to be the most important part. The important part is to break down this problem, figure out what we're talking about. So first of all, what is the original 2-digit number means we need to figure out what the 2 digits were. Now, the 2 digits are being used in ways that aren't even just outside the number, like using in the number itself, like the number, 76. I'm not using 70 all the time. Sometimes I'm actually using the 7, the sum of the digits. So here, let's use 76 as an example for all this thing. I have no idea what the answer is based on this. So 76 here, if this was my original number, and trust me, it's probably not. But when I add these 2 digits together, I'm getting the number 13. What they're saying is this number is 18 less than the number itself. So is 13 just 18 less than 76? Of course not. So this isn't the number here. 58 is 18 less than it. But they're saying if I added 7 plus 6 and got 58, oh, then that would be correct, right? So we're taking 7 plus 6 there, and we're saying 18 less than the number itself. So we're going to do one equation based on that info there. Not these numbers, but based on that info. When the digits are reversed, like 76 turns to 67, then the new number is 27 more than the original number. So 67 it's the same thing as taking 76 and adding 27? No, of course not. But the idea, again, is original number, new number. Adding 27 to original gets you new number when digits are reversed. So this whole thing's about digits. I don't know what the digits are. So I'm going to do a tens digit and a ones digit here. And we'll let x represent the number for the tens digit value. And y I'm going to represent as the ones digit. So I'm going to create two equations. I'm going to create two equations based on this information here. This first bit of information is saying if I add my digits together, 7 plus 6, x plus y, that's equivalent to taking the original two-digit number and subtracting 18 from it. So the real question here is, how do I make this a two-digit number? Do I write it as x dy? No, because this is x times y. So to use a tens digit, like 76, that's 70 plus 6, which is taking the digit, multiplying it by 10, plus 6. So I'm going to take x and multiply it by 10, 10x. And I'm going to add y to it. That is the original two-digit number. Take the two-digit number, subtract 18. That should match the sum of the two digits themselves. Now when I reverse the digits, so when I do 67, which is 60... Ignore that, which is 60. There will be another one in 5 minutes, which is 60 plus 7. 6 times 10 plus 7, that's taking y and multiplying it by 10. 10y plus x. When I reverse the digits, this new number is 27 larger than the original number. So the original number, 10x plus y, I'd have to add 27 to that number in order for this thing to even match up with the new number here. Here's my system of equations in raw form right there. Okay, that's raw form. If I want to clean this up a little bit, I'll combine like terms, get the x's and y. Y is probably on the same side of the equation, so maybe to the left side here. Treat it like an elimination problem. Top equation here, and so that's probably the hardest part. Now we're going to solve for x and y. Top equation, subtract 10x, subtract y. I'll get negative 9x equals negative 18. Look, the y's actually canceled. So look, even with this, I'm going to solve for x pretty quickly. Divide by negative 9, I get x equals 2. That's awesome. I've already kind of got this thing set up in a way that's going to help me out. Solve for y now. So the tens digit is 2. Solve for y now. Let's just write it from the bottom equation here. 10y plus x equals 10x plus y plus 27. So subtract y. Let's do that. 9y. Let's subtract this 2 on this side. 20 plus 27 minus 2. So 9y, and this better be a one-digit value. If these were two-digit values, that would be a problem. 9y equals 47 minus 2, which is 45. Y equals 5. So it's not just that the tens digit is 2 and the y digit is 5. By the way, these are for original number. This is for the original number. But the actual number itself, what is the original two-digit number? The original two-digit number, if the tens digit is 2 and the ones digit is 5, then the original two-digit number is 25. Let's see if that works out. First, we said that the sum of the two-digit number is 18 less than the number itself. 2 plus 5 is 7. 7 is 18 less than 25. Check. They say when you reverse the digits, 25 turns into 52. That's 27 more than the original number, 25 plus 27. 25 plus 27 is 52. That checks out. So there it is. The setup's kind of tough, but that's where you have to define variables and make sense of what it is you have. And by the way, this was for original number, right? The new number was y dx, right? The y is the tens digit at that point. There you go. Done with chapter 7. On to chapter 10. We are dealing with conic sections, parabolas, hyperbolas, circles, and ellipses. The world actually is elliptical, or it is an ellipsoid. It probably doesn't look like this, but the equator is a little bit longer than the prime meridian. It's actually not spherical. True fact. Number 1, find the vertex, focus, and directrix of the parabola x squared minus 10x plus 12y plus 37 equals 0. And I might draw it out as well to kind of make sense of some of these things if necessary. First of all, it's a parabola. We kind of know that because x it has a square, y does not. Okay, so if y isn't squared, let's isolate y here. I'm going to subtract x squared, add 10x, and subtract 37 to this side of the equation. 12y equals negative x squared plus 10x minus 37. Okay, in order to get this in vertex form here, I'm going to have to make this thing a perfect square trinomial somehow, which means it starts by factoring out that negative 1. I'm not going to divide by 12 yet. I'll save that for the end. Factor out the negative 1. I'm left with a positive 1x squared here. This will allow me to complete the square. Complete the square. I need a positive 1x squared to do so, and you could have done it on the left side of the equation to begin with, but this is important to note as well because this will run up in some problems here. Whatever I add here, I will also subtract here because I'm on the same side of the equation. But also note that a negative 1 is multiplying to these three things here. So whatever I add here, I subtract times negative 1, because this is going to multiply by negative 1, so this also has to multiply by negative 1. Okay, what's that number going to be? What I'm going to do is take this number, negative 10, I'm going to divide it by 2, that's negative 5. Negative 5 quantity squared is 25. This gives me a perfect square trinomial in here, and here I'm going to subtract 25 times negative 1. So 12y equals, there's a negative outside. This factors down to x minus 5 quantity squared, and this is a negative 37 plus 25. Hopefully I'm speaking over this enough so you can hear me. Negative 37 plus 25 is negative 12. So this becomes negative 12, and that's good because I'm dividing by negative 12 here. I'm dividing by 12 here in the end, and this vertex at least gives me an integer y value for the vertex. So y equals, this is negative 1 divided by 12. That's my stretch factor. I'm going to write that out in front here. That's x minus 5 quantity squared minus 1. Here's vertex form of my parabola, which does reveal the vertex to be the opposite of the h is 5, comma, negative 1. There's the vertex. I've answered one of my 3 questions here. I found the vertex. Boom. Now let's find the focus and directrix. And the focus and directrix has everything to do with my stretch factor here, my a value. By the way, there's another way I can write this equation. If you're doing this form, you're doing y equals a times x minus h quantity squared plus k. Other people might write this as y minus k equals a times x minus h quantity squared, or they might even do a in terms of p. Now, a and p have a special relationship. A is 1 over 4p, and you can also write p equals 1 over 4a. We may choose to use one or the other, all depending on what there is. P represents the distance from vertex to focus in one direction, and the other direction is distance from vertex to closest point on directrix. If a is 1 over 4p, you might see this equation in your book. Not exactly like this, not exactly like this, but if you multiply both sides by 4p here, you'll 4p multiplying by this quantity, y minus k, and that'll be x minus h quantity squared equals 4p times y minus k. Just like that. And this equation is something you'll see in your book at times, and you might be using this yourself, in which case we could rewrite this equation to say x minus 5 quantity squared equals 4 times p. We didn't get that number yet, by the way. We'll get that. 4p times y minus k. Y minus k, that's y minus negative 1, so that's y plus 1. Y plus 1, boom. So here's another way to write this equation. I'll give you that 4p moment, that value in a second as soon as we find p. So here's one equation. Let's get the other one. A equals 1 over 4p. A equals 1 over 4p. Well, a is negative 1/12. A is negative 1/12. Negative 1/12 equals 1 over 4p. Multiply both sides by 4p and both sides by 12. It's cross multiplication there. We'll get negative 4p equals positive 12. So 4p is negative 12. The reason I'm writing that is so I can give you this number right here. This number will be a negative 12 right there. Boom. So you can write the equation like this, and that matches up just fine. Now the p-value is something I still need here. P is negative 3. P is negative 3 means that the distance from vertex to focus is 3 down. My vertex is at the point 5, negative 1. Over 5, down 1. This is a y equals negative x squared parabola. So my parabola is going downward this way. They did not ask us to graph, so I'm not going to draw a perfect graph, but I will give you the example of the graph here. P being negative 3 means the focus is 3 down from this point. P is negative 3. I'll go 3 down from here. 1, 2, 3. Here's my focus value. That is the point 5, negative 4. There's the focus right there. The drawing helps. The drawing helps, especially when it's a fraction. But the drawing helps note which way you go. The directrix is going to be 3 up from there. 1, 2, 3. Here's 1 point on the directrix. I didn't draw this focus right. Boom, right there. I counted the calculations right. I just didn't draw the focus right. The directrix is a line. This line is going across. Boom, like that. Okay, that line is the equation y equals 2. So the focus is at 5, negative 4. The directrix is at y2. The vertex is at 5, negative 1. We have all 3 things that we needed for this parabola. Number 2, find the standard of the equation of the parabola with the vertex at 0, 0 and directrix x equals 7. And of course, when in doubt, draw it out. That's going to be a motto of mine I'm going to use for these kinds of problems here. Here's my vertex at the origin. My directrix is at x equals 7, 5, 6, 7. It's going to be this line right here. What I'm going to draw this stuff for is to help establish which way my my parabola faces. Okay, now this is a parabola because it has a directrix. It looks like it's going to face this way because of how the directrix is drawn here. It's going to be facing to the left, which gives me a couple bits of information. This is going to be an x equals negative y squared kind of equation, kind of guy. So it's either going to be x equals a times y minus k quantity squared plus h. Or if you do this written another way, you could be writing it as y minus k quantity squared equals 4p times x minus h, of course, like that. But the general thing is that a will be negative and p will be negative like this for this to work. We're going to get a negative value for a or p for this to actually pan out the way we want it to. Okay, so here we go. P is the distance from vertex to focus, okay, which if p is negative, we're going this way. This distance here is 7, so this distance here is 7. But technically here we're referring to negative 7 as far as p. We subtract 7 to get to focus from vertex. And they're not asking us to find the focus, but we did need the p-value. P-value is negative 7, and a is 1 over 4p. So a is is 1 over 4 times negative 7, which is negative 1 over 28. So this will help me for my equation on top or bottom. Okay, the vertex, by the way, is at 0, 0, hk. So this y minus k stuff and x minus h stuff won't matter. This will either say y squared equals 4p times x, or on this equation right here, we could write that as x equals a times y squared. Okay, so if I use the green right here, this will say y squared equals 4 times negative 7, that's negative 28x. That's one way of writing the equation. But you could also write it as, if you divide by negative 28 here, you can see x equals, a is negative 1/28, negative 1/28 y squared. Either here or here. It's the same equation, same answer. I prefer this. And look, I think this is probably the last time I'm going to use this stuff here. If you want to use it, feel free, go ahead. Try and know how to rewrite this to that or that to this if you're going to use that. I'm a little more comfortable using something in standard form. That's how I'd graph. I understand how the stretch factor works based on it, and we've been using it long before, and we'll be using it long after. Number 3, find the center of the ellipse. 5x squared plus 2y squared minus 20x plus 24y plus 82 equals 0. Okay, the center just requires that I know my standard form of my ellipse here, x minus h squared over, it might be an a squared, it might be a b squared, I'm not sure which one. I'm just going to put it this way to begin with. y minus k squared over b squared equals 1. This is the form I'm trying to get it to. Now, the larger number will be a squared, so whichever one this goes underneath would technically be a squared. And b squared would be the smaller number representing minor axis there. But here, that's not my focus. My focus is just focus. My intent is to figure out what h and k are. That's it. I don't need to draw this thing. Find the center. What I'm going to do is I'm going to group up my x's, my x terms, 5x squared minus 20x. And I'm going to group up my y terms here, plus 2y squared plus 24y. And I'm going to get this constant over on the other side, equals negative 82. Now to complete the square here, I need to make sure that I get a positive 1x squared. So I'm going to factor out the 5, get x squared minus 4x. We'll complete that square in just a moment. And then over here, for the y values, I'm also going to complete that square. So I'm going to factor out the 2, give me a positive 1y squared. Y squared plus 12y plus an unknown there. We'll figure that one out. And this all equals negative 82. And we're going to be, whatever we add on this side, we add to this side as well. Plus blank, plus blank. This blank here in blue will be the number, divide negative 4 by 2 squared is 4. So I'm going to add 4, but it has to be multiplied by this 5. 4 times 5. Right there. And then in green here, when I divide 12 by 2, that's 6. 6 squared is 36. I'm going to add 36 here, but remember it's multiplied by 2. There's a 2 over here. Now, will this stuff matter for my final answer? No, because my final answer says find the center. And this stuff matters for the center. But I will give you a final equation so we can see where we finally end up. Plus, it's going to matter for future problems. So 5 times, this will be x minus 2 quantity squared, plus 2, this will be y plus 6 quantity squared here. That equals negative 82 plus 20 plus 72. Okay. Now, I already know the center at this point, so maybe I will stop here, but I'll tell you what you would do next. The center is going to be at hk, 2, negative 6. That's the answer. Okay. Now, if you did want to do the rest, you'd combine like terms here, and then you divide by whatever number this is. Negative 62 plus 72, that would be 10. This would be 10, and you divide these by 10. Yeah, let's figure that out. That'd be x minus 2 quantity squared over 2. 5 over 10 is 1/2. Plus y plus 6 quantity squared over 5. That's 2 over 10 is 1/5 equals 1. The center's at 2, negative 6. Major axis derivation, minor axis derivation. Find an equation of the ellipse with foci at 0, 2, and 0, 8, and vertices at 0, 0, and 0, 10. When in doubt, draw it out. Foci will be purple, vertices will be green. Hey, why not? Foci at 0, 2, and 0, 8. Vertices at 0, 0, and 0, 10. The center, well, okay, first of all, vertices is in reference to major axis. Co-vertices would be in reference to minor axis. The center, oh, and also by major axis, foci are on the major axis. The center is going to be in between these things, either between 0, 2, 0, 8, which is 0, 5, or between 0, 0, and 0, 10, which is also 0, 5. So the center is at 0, 5, and the reason I need that is because I need an equation. The equation means I need h and k. Well, h is 0, k is 5. The other things I need are a squared and b squared. Well, 2a is this entire length right here. 2a is 10, the distance from the distance between vertices. Major axis length. Semi-major axis length, a value is 5. If a is 5, a squared is 25. I need that value for my equation. I also need my b value here. I need to figure out what b squared is by figuring out what the minor axis length is or what b is or anything like that. Now, I'm not going to draw that stuff. In fact, I did all that I really needed to do with the drawings here, except for also representing c. 2c is the distance between both foci. C is the distance from center to one focus. That's going to be 3. So c is 3, c squared is 9. This is important because to find b here, I'm going to be using almost Pythagorean theorem looking equation. It's going to be a squared equals b squared plus c squared, or of course you can write, you can rewrite itself for b. You can c squared is a squared minus b squared. Subtract c squared though to get b squared. We'll get b squared is a squared minus c squared. B squared is a squared minus c squared. We know a squared is 25. We know c squared is 9. So 25 minus 9 is 16. I don't need to know what b is. I need to know what b squared is. I need to write my equation of my ellipse. Final thing I need to do is state that my major axis is vertical. Okay, that's important to know which variable a squared goes under. Apparently it's going to go under y because the major axis is vertical. So my center is at 0, 5. So it's x minus 0 quantity squared over, which is x squared. I'll just write that. X squared. Whoops. X squared over b squared over 16. Minor axis is horizontal. So x squared over 16 plus, for an ellipse, plus y minus 5 quantity squared all over a squared, 25. This equals 1. I don't use c squared in my equation, but I used it to get b squared, which is in my equation. There's your final answer. Number 5, find the standard form of the equation of the hyperbola with vertices at 6, 3 and negative 2, 3. And with asymptotes, y equals 3/4 x and negative 3/4 x. Basically plus or minus 3/4 x. First of all, what's really good about this, this set of equations here, actually, you know what? I take that back. I'm taking a look at this and saying this might not be our answer. There's supposed to be more to this equation than we see, which is kind of unfortunate that we don't have. That's probably why there's a space. The y-intercept should probably be here. I was going to say, the good thing about this is knowing that the center's at the origin because these two intersect at the origin. But seeing these vertices here, when in doubt, draw it out. 6, 3 is right here. Negative 2, 3 is right here. These are your vertices of your hyperbola. Our center is not at the origin here. No, it's not here. Our center is in between these two vertices. So, unfortunately this thing doesn't have a proper y-intercept. If possible, I will see if I can provide the proper y-intercepts for you. That's not going to be my focus. My focus will be the equation here. Now, the center's in between 6, 3 and negative 2, 3. You can count it out. 8 is the distance. Halfway in between is 4. Your center is at positive 2, 3. Center's at positive 2, 3. Our asymptotes, I'm going to stem from that center equation there. Up and down 3/4 and stuff like that. Center's at 2, 3. That's my h and k value right there. Important for my equation. I also need a squared and b squared just like I do for an ellipse. Now, a represents the transverse axis. The transverse axis is the axis with your vertices on it. This hyperbola is going this way, left and right. That's the direction of the opening, left and right, because that's where my vertices are. Now, there's a central rectangle idea that I need to do to create the hyperbola, or better yet, to determine what b is here. Now, I don't know my foci, so even if I can figure out a, which is 4, and a squared, which is 16, for my equation, I won't be using the foci to find out b, but I'll be using my asymptotes to find out what b or b squared is here. So a is 4. I go 4 units that way. And also my asymptotes here, I can rise 3 from my center and run 4. And I have this corner of my central rectangle of that box here. Fall 3, run 4. You can do the same thing here. This is that 3/4 x slope they were referring to here. So there is an asymptote that's going across, let's see, kind of like this right here. Okay. So there's an asymptote there. There's a second asymptote that has a slope of negative 3/4 from center that's going this way. Whoops. It's going this way and this way right here, down 3/4 to create that central rectangle again. It's going kind of around like this. Okay. Now, luckily, this is the actual central rectangle, meaning it's going through the vertices. I don't think we'd ever be harsh enough, especially for a final for now, to create asymptotes that don't quite meet at your vertices there, but it's possible to do. I've provided homework problems with stuff like that. It's possible. Anyway, this does verify that this is your central rectangle. Again, your hyperbola, kind of goes in this direction here and here, but we've now established our b value based on this. If the a value is 4, that represents distance from, these two, from the center to a vertex, then b value represents distance from center to the end of the central rectangle on this end. Your b value is 3. It's going up and down 3. B. So b is 3. B squared is 9. I found hk, a squared, b squared. That's enough for the equation, but I also need to know where a squared and b squared go. If this opens up these two directions here, left and right, okay, and that's not the perfect drawing. If I have to graph one later, I'll give you a better one. But then that means that the transverse axis, which is horizontal, means a squared. A is in reference to the transverse axis, and the positive squared variable is the transverse axis one. So x will be positive. Positive x minus 2 quantity squared over a squared, minus the conjugate axis is the other one. It's the negative variable, minus y minus 3 quantity squared over 9. That equals 1. A is not necessarily the larger number for a hyperbola. It could be. Not always. That's what we needed. We needed the standard form of the equation. Boom, just like that. You could expand this out and multiply by things as well. I'm just going to leave that as is right there in graphing form. Now, like I said, this thing right here, this should have had a proper y-intercept value. It's not like it runs into a perfect number, but it runs into 1, 2, 3, 4.5, up 3 over 4, up 1/2 over 2. So 4.5 right there, 4.5. I could write that as 9 over 2 if I want to write it as a fraction. That should have been there. Right here, this should be plus 1.5, which is 3/2. These are the actual equations right here. It's not just 3/4x and negative 3/4x. It doesn't cross through the origin. So kind of a mistake on the end of what's being typed here. Number 6, classify the graph of 3x squared plus 2y squared minus 6x minus 2 equals 0. They're asking you to find out what kind of conic this is. What kind of conic this is. Both variables are square. Here, let me do this. I'm going to type out the 4 different ones there are. And I'm going to copy and paste this for later because I'm going to use this later. And let's play the process of elimination. Instead of just knowing what it is, let's also play what it can't be. Oh, let me copy this. Okay, so parabola, ellipse, circle, hyperbola, which of the 4 is this conic? It's not a parabola because both variables are squared. It's not a circle, excuse me, it's not a hyperbola because both variables have the same sign on the same side of the equation. In this case, as we want them to be both positive. It's not a circle because the coefficients for the squared variables are different. Therefore, it is an ellipse. Squared variables, both same sign on same side, both positive in this case, and different coefficients. If they're the same coefficients, it would be a circle. Number 7, classify the graph of. Copy, paste. Boom. Let's find out what conic this one is. Okay. Not a parabola because both variables are squared. Not a circle because of the different coefficients there, but also not because same reason it's not an ellipse. It's different signs for these two squared variables on these sides, same side of the equation. This is a hyperbola. Number 8, eliminate the parameter and find a corresponding rectangular equation. Okay, so for this kind of problem here, there's also a hint that we can throw out for you that has to do with basically getting rid of the trig functions here. Let's use the idea that sine squared of theta plus cosine squared of theta equals 1 for this to become rectangular or Cartesian, system, Cartesian coordinate system. Here, using only x and y basically. There's no theta, no t, nothing like that involved from parametric. So in order to use this right here to make something equivalent to 1, let's get these things so that cosine of theta is written by itself. It's isolated. Subtract 3, cosine of theta would equal x minus 3. Sine of theta when isolated would equal y plus 1. So if cosine squared of theta plus sine squared of theta equals 1, I can rewrite these things and substitute them in place of this, and I can rewrite a corresponding rectangular equation that uses only x and y, and just maybe it's probably wise to get y by itself, so you could even graph them to compare. If sine of theta is y plus 1, sine squared of theta is y plus 1 quantity squared. If cosine squared of theta is cosine of theta is x minus 3, cosine squared of theta is x minus 3 quantity squared. This equals 1. Now, here's a nice rectangular equation in itself. You could be done and say, hey, this is an ellipse, and we could graph this and all that. That's fine. So you could keep this like an ellipse right here. If you also want to, however, if you want to graph it in your calculator and confirm that it's correct, then you could get y by itself. So this is a proper answer. Probably better if you write the x first because we're used to that. This could also be written as over 1. What I'm going to do also is get y by itself here. So I'm going to expand this. Y squared plus 2y plus 1. Actually, I don't want to expand y. If I want to get y by itself, I want to keep it like that. Let's expand x, though. Actually, now, you know what? Let's not expand either. Let's get x on this side. Subtract it over. 1 minus x minus 3 quantity squared. It's fine to leave it like this. Square root both sides now, though. Right? Because if I want to get y by itself, I'm going to make it say y plus 1. Now, y plus 1 equals plus or minus the square root of 1 minus x minus 3 quantity squared. This cannot simplify, by the way. You can't make the square root of 1, 1, and just x minus 3. Doesn't work that way. Subtract 1, you get y equals negative 1 plus or minus the square root of b squared minus 4ac all divided by 2a of x minus 3 quantity squared. There's the final answer there. This is a half dome for negative 1 plus. Negative 1 minus is another half dome there. It gives you an ellipse. That is the same thing as in parametric form, x equals y equals with these two variables here. Try in your calculator. They should work. I'm going to move on for the sake of time. This equation could and should probably be okay. Depends on what they mean for this stuff here. A standard form, graphing form, this form, I don't know. But either or can work here. Number 10, there's no number 9. Number 10, convert from rectangular to polar coordinates. So your x value is negative root 6. Your y value is root 2. Polar coordinates would give you a magnitude and direction here. R would be the distance, kind of that hypotenuse of these two when drawn, and direction theta. So negative root 6, it's between root 4 and root 9. So it's between 2 and 3. So let's just say it's kind of around right there. It's negative root 6 over. And root 2 up is between, 1 and 2. It's around, what, 1.4 or something. So kind of up here, it's negative root 6, and root 2 is up right there. So R is this distance from origin to here. This is your R value, that length. This is polar coordinate form if you use R. And theta is this angle right here. Either in degrees or radians, we can determine what that's going to be. So R, if we use kind of Pythagorean theorem here, R squared is x squared plus y squared. So R is the square root of negative 6, root 6 quantity squared plus root 2 quantity squared, like that. R is the square root of 6 plus 2. R is the square root of 8, which can be simplified to 2 root 2. So R's magnitude is 2 root 2, like that. Okay? Or you can write absolute value of R if you so wish. Okay, so magnitude of R there is 2 root 2. The direction theta here, I'm going to start by doing kind of a theta prime. Let me kind of redraw this triangle that you see there. I have root 6 over root 2 up, and we have theta going this way that we can find if we find this theta prime from within. And it's good to draw these things out so you know where you're at, which quadrant you're in, and kind of how all this is going to work here. Now, we could use a calculator for this, absolutely, but we also know this is 2 root 2, and maybe, just hopefully, you could even find a connection here. This is 2 times larger than this short side here. This is actually negative root 3 times larger right here. This is the same relationship that you see in a special right triangle with the relationship here of 1 to 2 to root 3, or even negative root 3. This is a 30-degree angle. Theta prime is 30 degrees. If you're not convinced by that, or if you don't know what I was talking about with that, or you want to trust your calculator more so, make sure you're in degrees with this. Okay, hang on, my calculator froze up. Okay, there we go, I had to reset it. Make sure you're in degrees, okay? And when you do this here, what we're going to do to find theta, let's take a look, or theta prime, still on theta prime here. Theta prime, if I take the tangent of it, let's use these two numbers. Tangent of theta prime is root 2 over negative root 6. Now again, you could probably still find this out without a calculator doing this, because tangent of theta prime that's negative root 2 over 6, so negative root 1 over 3 or negative root 3 over 3. You might know that stuff as well. But anyway, I'll use the top two right there. So theta prime is the inverse tangent. Theta prime is the inverse tangent of negative root 2 over root 6, like that. If I leave it like that, then at least I trust that no math issues along the way. So I'm in degrees. I'm going to do root 2, or negative root 2, over root 6. Close this parenthesis here, and then try the next one. Okay? And then I'm going to get this number here, negative 30. Now, negative 30 is just, it's going 30 from 180 because inverse tangent on your calculator only knows between negative 90 and positive 90. So we're just going to have to work with knowing what the reference angle is referencing, literally. This is a 30-degree angle here. Okay, which means theta here is the supplement of 30, which is 150 degrees, or 5 pi over 6 radians. So there are two ways you can answer this question. Number one, 2 root 2 for polar coordinates, 2 root 2 for r, and 150 degrees for theta. Or number two, 2 root 2 for r, and 5 pi over 6 radians for theta. One or the other. Magnitude, direction, polar coordinates. Number 11, convert from rectangular to polar coordinates. We got 0, negative 4. Okay, so this point on the graph, so we're aware, 1, 2, 3, 4 is down here. So, there's some different answers that you can arrive at with this thing here. To start with, our r value, it looks like it's 4 here. I'm going to show you an answer when you use negative 4 with it as well. But if your r value is 4, then your theta value is this long thing right here, if we're looking for r and theta. So theta is this long guy right here. I don't really need to use inverse trig for anything here, and your calculator won't give it to you because inverse tangent of 4 over 0 won't help you. But anyway, so this degree here is 270 degrees. Theta is 270, which is also 3 pi over 2. So one way to answer this question is to use magnitude of 4, the positive version, and 270, or 4 comma 3 pi over 2. That's polar coordinates. Or let's say you wanted to keep that 4 negative. What if you want to say, hey, I'll deal with a negative 4 here, which kind of changes the idea of the direction here, because you would start technically just by going only this amount in terms of theta, and then you'd flip it over to make that the negative 4. So if you're going to flip this over as a negative 4, if r is negative 4, then you're only going 90 degrees here. Theta is 90 degrees, or pi over 2 radians there. So another way to answer this one here with a negative, which I prefer my magnitudes positive though. However, if you had to stay within a certain domain, you might do this instead. So 4 different possible answers here. I think any would be right. So, and the thing is, the problem with this is your final review, so multiple choice, right? Any one of these answers could show up. So you want to be able to see all of them in play. Number 12, classify each conic section. Copy, paste, parabola, ellipse, circle, hyperbola. For A, both squared variables, out. Negative and positive, different signs of my squared variables, out, hyperbola. A is hyperbola. B, both squared variables, parabola's out. Both same sign on same side of equation, hyperbola's out. Same coefficient of 1 means circles in, ellipses out. B is a circle. And look, I don't have to do anything else with this problem as long as there are no other x squared, as long as they don't trick me and show another x squared here or something. That's exactly all I have to do. 12c, here we go. 25x squared plus 9y squared. Let's two squared variables, same sign on same side, so that's out. Different coefficient, so that's out. Ellipse is in. It's in style, at least for 1 second. And D, right here. Not squared variables, out, in. You don't even need to know anything else about same sign and coefficient and anything else. This is a parabola. Just classifying, not graphing, not finding equations of. Just boom. Classify each conic section, write its equation in standard form, and sketch its graph, part A. So part A is a circle because same coefficients, squared variables, and same sign on same side of the equation. That's 1x squared, 1y squared right there. So it is a circle which means our equation we're going to look for will look like this. X minus h quantity squared plus y minus k quantity squared equals r squared, where the center's at h and k and the radius is r. Let's group the x's together here. X squared minus 8x. Let's complete the square plus blank. And then I got plus y squared plus 2y plus blank. This will equal 13 plus a blank plus a blank. Nothing else to multiply with those. Just complete these squares and keep working on. At this point now I get to do a little more of a rushing mode now that we're kind of in the groove. Divide by 2 and square it, we get 16. This will be a 16. Divide by 2 and square it, we get 1. This will be a 1. This factors down to x minus 4 quantity squared plus y plus 1 quantity, y plus 1 quantity squared equals 13 plus 16 is 29 plus 1 is 30. So your center, so here's the equation. Your center is at 4 comma negative 1. Your radius is the square root of 30, and I don't think that can simplify anymore. So square root of 30 is between square root of 5 and 5 and 6. Square root of 25 and square root of 36. So I'm going to graph it around 5.5 there. Yeah, I'll just leave it like that. Okay, so 4 negative 1, sketch its graph, over 4 down 1. Root 30. I'm going to go around 5.5 up, down, left, right. You can use your calculator to get a better approximation than I'm going to have here. Okay, say there, 1, 2, 3, 4, 5.5. Good, it just fits. 1, 2, 3, 4, 5.5. Get these 4 points in, and then draw your best circle you can. Because I'm getting kind of wobbly with my with my curves and stuff. I'm going to use the circle tool and draw it in green, and just finish off right there. Close enough. So there's my circle. That's number 13, part A. Part B, classify what kind of conic it is. Well, this is an ellipse. Squared variables, different coefficients, same sign on same side. This is an ellipse. So I'm going to look to make an equation that looks like x minus h quantity squared over, and look, this one's actually going to be a b squared this time. I just knowing the coefficients here, that'll happen. It'll be smaller. Plus y minus k quantity squared over a squared equals 1. Basically, even if I was wrong here, and I very well could be, who cares? The a squared would be the larger number. Look, we're going to graph it based on that anyway. So the important thing is knowing how to graph it based on this. So here we go. Let's complete squares here. 9x squared already is a perfect square here because there are no other x terms. I'll leave that be. With the 4y squared and 8y's, they're already grouped together. Let's go ahead and factor out the 4 here, make us a 1y squared so we can complete this square inside. I'm going to add the 140 to the other side, and I'm going to add the same thing over here that I added right here, and that was times 4. So this will be 4 times that number. Y squared plus 2y, this will be plus 1, divided by 2 squared. This will be a 1 over here times 4, add 4, add 4. So now we have 9x squared plus 4 times y plus 1 quantity squared, that's what that factors down to, equals apparently 144. To get this in that perfect elliptical form now, let's divide everything by 144 and hope that everything can reduce how we'd like it to here. 9 over 144 reduces to 1 over 16. So this is x squared over 16. 4 over 144 reduces to 4, 30, 40, 46? 46. Is that right? No, 36. Okay, over 36. I was going, that's a weird number. 36 equals 1. Boom. So we have our equation. Now let's go ahead and graph it based on what we understand here. A squared is in reference to 36, so A is 6. A is going to go up and down 6 from center. We have to figure out the center as well. A has to go up and down 6 from center because it's underneath Y, so that's the major axis. B squared is 16, so B is 4. Okay, so we're going to go left and right 4 from center. Our center is at 0 for x, negative 1 for y. So starting at 0, negative 1, let's do those things and draw the graph. Starting at 0, negative 1, let's go up and down 6, and left and right 4. Boom, 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 boom. And let's draw an ellipse based on that. I think I have a tool that can help me out with that right here. Let's make it blue. And we have our graph right there. All right, so major axis was vertical there. Letter C, y squared over 25 minus x minus 1 quantity squared over 16 equals 1. Okay, this is already in its standard form to graph. This is a hyperbola. Squared variables, okay? Squared variables, opposite or different signs, doesn't matter if these coefficients are the same or different. In a hyperbola, let's dissect the center. The x value for the center is 1, the h. Y value for the center is 0, that's k. We're going to start at the point 1, 0 for center. This is not a point on the graph. This is a feature to help explain our graph. Our transverse axis is vertical. Your a squared goes with the positive number always, not necessarily the larger one. In this case, it is larger. A squared is 25, so a is 5. We will go up and down 5 because it's under y. This is a vertex, and down here is a vertex as well. B is in reference to the 16 here. B squared is 16, so b is 4. I will go left and right 4 to help create my central rectangle, which helps establish those corners so I can draw my asymptote. Here's 4 to the left, 4 to the right, not points on my graph. These corners are what matter most here, where A and B kind of meet if you draw horizontal and vertical lines. Here's a very pretty central rectangle. They did not ask us to find the equations for the asymptotes. We could find them. They do not ask us to. So I will not. But I will draw the asymptotes. That's to help me make my graph here. So the asymptotes go through the corners of the central rectangle and through the center, collinearly with the center of this graph here. Looks like we 1, 2, 3, 4, rise 5, run 4. As I rise 5, run 4 this way. This asymptote goes forever, up, down, up, right, and down, left. This asymptote here is negative 5/4, like so, and I'll extend those ones as well. Up 5/4, down 5/4, stuff like that. So there's this one, goes on forever. This helps me with my great, now I just asked. This helps me with the asymptotes help me with my hyperbola because I know the vertices here, the direction of opening is up, down, and left to right, and it approaches the asymptotes here. Remember, hyperbolas are more so linear than they are parabolic. Although they curve here, they don't increase with that quadratic fashion. They increase more like a slope because they start to approach the asymptote here and over here. Okay, so up, down, boom. And they should be approaching, never crossing, never touching, and also, but especially never diverting away from. They should be getting closer and closer. Okay, and we land on chapter 12. This is the last chapter, and this one focuses mostly on things you would actually see in calculus, where you have derivatives, you have limits, you have these other things called integrals we will lightly touch on. And I get a kick out of this one all the time, Optimus Prime. And this is from Mean Girls, of course. The limit does not exist. And we're going to run into, I think, some answers along the way that actually say that. And that is true. The limit of this does not exist. All right, use the graph to, this is part A right here, number 1. Use the graph to find the limit of the function if your piecewise function is as such. And it's graphed here. 3 minus x, if x isn't 1, it would look like this line here going on forever. Except when it's 1, it's going to have a hole. It's going to jump it because we don't know. We don't have anything defined for it until you look down here. Apparently it's defined at 1 when x is 1 here. But we're going to see what the limit is as x approaches 1, meaning coming from the left and the right side of 1, what is it closely approaching here? So the equation says one thing, the graph says another thing here. The defined value of 1 for x is, for y, when you plug in 1 for x, the defined value is 1 for y. But as we approach 1, as we get closer and closer to it and use your graphing calculator, you can see you're going to be approaching the number 2. The limit as x approaches 1 of f of x is 2 because that is the y value that it's getting closer to from our defined set, even though the defined value is at 1. B, use the graph to find the limit as x approaches 0 of f of x. So this is a new function. We don't have the equation here. It's kind of broken, but what you see here, the graph is broken. It's supposed to be. The axes aren't. But what you see here is approaching from the left and from the right that we are approaching 2 different sets here. The defined value at 0 very well may be 2. That might be a closed circle here. But coming from the left, it is approaching 2. Coming from the right, it's approaching 1. So the limit as x approaches 0, the left-hand limit of the function is 2. The limit as x approaches 0 from the right side of this function is 1. So if they're approaching two different things, or if they don't approach the same thing, or as Lindsay Lohan said, if they don't approach anything, the limit does not exist. The limit at that value. Left and right hand limits, they may have one, but if they're not the same number, then the limit does not exist. Number 2, find the limit as x approaches -2 of this guy right here. Now this is a polynomial, it's a quadratic, which means I'm going to try and substitute -2 into here and see if I have any issues doing so. Sometimes the limit just approaches the same thing as its defined value. That's actually perfectly okay. I think most of us prefer that instead of approaching something differently like 1a, you know what I mean? So -4 minus 3 is -7. So the limit as x approaches -2 of your function is the same thing as the defined value. When x is -2, f of -2 is -7, and when you approach it, you're approaching -7 for y as well. Number 3, find the limit as x approaches pi of x over cosine of x. So again, substitute to see if there are any issues with what you have here. This will be pi over cosine of pi. Now you can use a calculator at sometimes, it depends. But here, cosine of pi over on this side here, that's almost like a triangle. Like that guy right there with a -1 and 0 and 1. -1 over 1 is -1. Pi over -1, which is negative pi right there. You can also think of your trig graph. Pi, -1, boom, right there. Sorry for all the scrappy work, but there are a lot of ways you come up with it. You can use your calculator, of course, as well. Number 4, find the limit as x approaches 2 of 3x cubed minus 4x squared minus 5x plus 2 over, all over, x squared minus x minus 2. First thing I'll try and do is see if this works without any simplifying needed. And if it does, then that's the answer. See, rational functions, though, have the potential to divide by 0. And if you get 0 over 0, then that means that we can still find its approaching value, and there won't be an asymptote. Instead, there will just be a hole. So let's see what we get here. This is going to be 2 cubed, which is 8, times 3 is 24, minus 2 squared, which is 4, times 4 is 16, minus 10 plus 2, all over 4 minus 2 minus 2. So it looks like the bottom's an issue. We're dividing by 0. The top, 24 minus 16 is 8, minus 10 is -2, plus 2 is 0. So indeterminate, defined value. But we can still determine its what do you call it? We can still determine its limit by simplifying this stuff here. Now the top has a few concerns here because there is no what do you call it? There is no you can't factor by grouping. There's no common factor between these terms and these terms as well. The bottom looks like it can factor that just fine. So this is x minus 2 times x plus 1. Here's what I'm going to do with the top. The assumption and the knowledge of 0 over 0 means that x minus 2 is a factor on top. X minus 2 is a factor. We have to know that because it has to cancel out with the bottom x minus 2 for us to make this work. And it's not that it has to work in all cases, but in this case, 0 over 0, it does. So you factor x minus 2 out of 3x cubed minus 4x squared minus 5x plus 2. You can use synthetic division or long division, and you can determine what the other polynomial, what the quadratic version of this polynomial should be. That's a positive 2. And it looks like it'll be 3x squared, this is x minus 2, times 3x squared plus 2x minus 1. Now, there's no requisite for this thing to factor. All we need to do is know this thing cancels. So this is the limit as x approaches 2 of this right here. Now we can substitute 2 into here and not have a hassle. Whether or not this factors is irrelevant to me. I'm just going to substitute in right now. So this equals 3 times 2 squared plus 2 times 2 minus 1 over 2 plus 1. So let's see what it was going to be approaching. You can use your graphing calculator to see this as well to confirm this. 12 plus 4 minus 1 over 3, which is 15 over 3, which is 5. So the limit as x approaches 2 of the original function is 5. That is the y value that this was approaching. You can see your graphing calculator. Let's take a look at that. Okay, number 5, find the limit as delta x approaches 0 of the square root of x plus delta x minus the square root of x all over delta x. Okay, delta x is, excuse me, literally the same thing as h here. If you're like, well, this is hard to do. Well, it's the same thing as h. It's limit process. H is literally the width of the distance between your x value and an x value that is so insignificant, or the value is so close to it that the distance between them is so insignificant, might as well be 0. Now, the issue with this, of course, as you begin is you see that we divide by 0. It's actually 0 over 0, which is an indeterminate. So what we need to do is figure out what it's approaching from both sides. And this is for any change in x and for any x value here. So given this function. So what we're going to do is find a way to cancel what's on the bottom here. And that really works through simplification matters, such as this numerator being irrational. We can work to rationalize it by multiplying the top by its conjugate. X plus delta x, or square root of x plus delta x plus square root of x all over square root of x plus delta x plus square root of x. Multiplying by 1 here on the top, I'm going to be able to FOIL or distribute, the stuff. It's a difference of 2 squares problem. This times this just equals x plus delta x. So this is x plus delta x. That's the first 2. Then this multiplies with this, and then this multiplies with this, and they're negative and opposite versions of each other, and then they cancel. And then you get negative root x times positive root x, which is negative x. So minus x. This all divides by this whole set right here. Delta x times the square root of x plus delta x plus square root of x. Now I'm not going to bother I'm not going to bother distributing this stuff right here. The whole intent is to cancel out this thing on bottom that's making me divide by 0. So x minus x goes away, thankfully, and now we're just left with just delta x, and that's a common multiple on top with bottom. These now get to cancel, and on top you're left with 0. Just kidding, you're left with 1. On top you're left with 1. On bottom you're left with this junk down here. The good news is I can now substitute 0 for delta x and figure out what this will become. This is 1 over the square root of x plus 0 plus the square root of x, which is 1 over square root of x plus square root of x, which is 1 over 2 root x. And look, I'm not going to bother rationalizing right there. I'm going to keep it like that. That's fine. When you do actual derivatives in calculus, you're going to leave it like this as well. You'll be okay with it. Rationalizing in this case would almost be moot. If you write final answers plugging in numbers for x, okay, I can see where you rationalize. But for now, keep it like that. Number 6, find the limit as x approaches 1. I think that's a 1 from the positive side of 1. That doesn't mean positive 1, although it is. Of root x minus 1. Okay, just like last time, what we're going to do is see if substituting 1 into there affects anything majorly. This 1 minus 1 square root of 0, which is 0. Okay, this is the defined value of y when x is 1. And we're testing from the right side. They're basically saying for this square root graph, which would look kind of like this right here. Here's 1, and it's going to go wee out like that. It says coming from the right side, what value are we approaching for y as x gets closer to 1 from the right side? And that number is 0. And that's all there is to it. There's actually not more. It's the same thing as finding f of 1 in that case. Now, there is no left side. There is no left-hand limit in this case. So the limit does not exist. But the right-hand limit does in this case here. Number 7, use the definition of a derivative to calculate the derivative of f of x equals negative x squared plus 2. Okay, to begin with here, the definition of derivative in terms of using the limit process here, we're going to find the slope of the line that's tangent to the curve at any x value here. So we're going to take a y value that's really close to our other y value, y2 minus y1, over h becomes x2 minus x1. This is limit process. This is how we would do it and calculate it. Sorry, this is limit as h approaches 0. So let's go ahead and do that. F prime of x equals limit as h approaches 0 of f of x plus h. That is negative x plus h quantity squared plus 2. minus f of x, which is negative x squared plus 2. This is all divided by h. Let's expand this, and let's distribute this into here. This will be f of x, f prime of x equals limit as h approaches 0 of the opposite of x squared plus 2hx plus x squared, plus h squared plus 2 minus negative x squared, that's plus x squared minus 2. This is all over h. And this equals the limit as h approaches 0 of negative x squared minus 2hx plus h squared plus x squared minus 2 all over h. Okay. Negative x squared plus x squared gone. I'm missing a lot of terms here. Hang on. Let me rewrite that. Let's do it on the bottom. I thought I was running out of room. Let's do that one more time. Sorry. F prime of x equals limit as h approaches 0 of negative x squared minus 2xh, or hx, minus h squared plus 2 plus x squared minus 2 all divided by h. Okay, here we go. Negative x squared and positive x squared are gone. They cancel. 2 minus 2 are gone. They cancel. You're left with negative 2 xh on top minus h squared all over h. And let's simplify that thing down now. Let's factor out an h on top. And you're left with negative 2x minus h on top, all divided by h. Now that we have a common multiple of h on top and bottom, now we can cancel. Now this thing, now we can substitute for 0 for h. This will be negative 2x minus 0, which is negative 2x. So f prime of x, the derivative of our original function there, is negative 2x. And there it is. And that represents any number I plug in for x, I can determine the slope of the line that's tangent to the curve at that same x value. Number 8, find the limit as t approaches, as increases without bound, as t approaches infinity, of 3 over t minus 2t over t plus 3. Okay, for number 8 here, what I'm going to do is substitute infinity in a way here, at least into this one. This one here, what I'm going to do is talk about dominance. And the idea here is that these are both t to the first power. So it doesn't matter if the 3 is here. This can be ignored and rejected. This would be infinity plus 3, which is basically infinity. So this is basically 2 times infinity over infinity. 2 times some number divided by the same number. That's basically, the t's cancel as well. You're basically minus 2 here. Okay, so that's that order. This is the dominance there. 3 over infinity might as well be 0. So this is 0 minus 2, which approaches negative 2. You can try it on a calculator, try and plug in a very large number and see how that results. You'll get the same thing. Number 9, calculate the limit as x approaches 2 of 2x squared minus 6x plus 1. As we did before here, I can just substitute 2 into here and see if I have a defined value. As long as it's a polynomial, you know, I really should. So here it's going to be 4 times 2, which is 8, minus 12, plus 1. Negative 4 plus 1 is negative 3. And that is the limit as x approaches 2 of this value. It's also the defined value for y when x is 2. There's a point on your graph that's 2, negative 3. Awesome. Number 10, find the limit as x approaches 5 of pi times a cotangent of pi times x over 6. This equals the cotangent of 5 times pi over 6, 5 pi over 6. Cotangent of 5 pi over 6, that brings us back to chapters 4 and 5. 5 pi over 6 is 150 degrees. 150 degrees is over here with a 30-degree reference angle. Whoa, in the second quadrant, right there. Which gives about a 1 to 2 to root 3 relationship, where root 3 is negative as it goes to the left. Cotangent is adjacent over opposite, so that's negative root 3 over 1, which is negative root 3. That the defined value is equivalent to the actual value. Very nice. Number 11, find the limit as x approaches 1 of this stuff here. This is a rational function. Let's test it first and see if we get a defined value. If we don't, we're going to have to do extra work if we can. 1 plus 1 is 2, minus 2 is 0. 1 minus 1 is 0. We have an indeterminate, which means there's a hole, And we can see what it would have been approaching from both the left and right side if there wasn't this hole. So we can recreate this equation without the hole here and then substitute in 1. On top, x squared plus x minus 2 factors to x plus 2 times x minus 1. This is limit as x approaches 1. Okay, this is on bottom I have x minus 1, which is a common multiple on top and bottom. These can cancel. You're left with the limit as x approaches 1 of x plus 2. Substitute 1 into x now that you're allowed to. We're going to get 3. As this graph here, which is linear, by the way, quadratic divided by linear, as this linear x plus 2 looking graph gets closer and closer to 1, your y value for this function gets closer and closer to 3. Number 12, find the limit as x approaches 1 of this guy. This is irrational and a fraction. All right, let's start by substituting in 1 here. See what we get. 1 minus square root of 2 times 1 quantity squared minus 1 all over 1 minus 1. This is 1 minus square root, let's see. 1 squared is 1 times 2 is 2 minus 1 is 1. Square root of 1 is 1. We get 1 minus 1 over 1 minus 1, which is 0 over 0. It's an indeterminate. We have more things to do. Let me get this stuff out of the way because it's just going to be, I assume this is going to be a long problem here or thereabouts because we have, well, actually, maybe not. What happens with these kinds of problems here is you hope that when you rationalize, let me try this. You hope when you rationalize the numerator here that they clean up everything for you so that you're left with a nice and pretty x minus 1 factor on top that we can then deal with. So if we do this here, where we multiply by the conjugate, 1 plus square root of 2x squared minus 1, on top we'll get that difference of 2 squares thing going. 1 squared minus this guy squared. The square root of something squared is just that thing, so minus this quantity right there. On bottom, I will leave that untouched and just multiplying this by this. Again, I want to cancel out x minus 1 as soon as humanly possible. Okay, so on top now, it looks like I'm going to do 1 minus 2x minus negative 1. So that'll become 1 minus 2x squared, then that plus 1, we're going to do 1 plus 1, which is 2 right here. On bottom, we have this stuff. Okay. If you're really still trying to look for that common factor of x minus 1, factor out a negative 2 from the top. Negative 2, x minus 1 is on top. Now on bottom, we get an x minus 1. It looks like it's going to clean up enough for us that we can now substitute 1 for x as need be. If only I could make straight lines. All right, so x minus 1 factor on top and bottom cancels. Awesome. Now we get to substitute in 1 for x. By the way, this whole time I should have been saying limit as x approaches 1. Limit as x approaches 1. That gets lost when I'm doing an explanation. If I'm doing the problem itself, I'd remember it. But at this point, excuse me, at this point now that they're canceled, I could substitute 1 for x and not have to divide by 0. No hole there anymore. Negative 2 over 1 plus the square root of 2 times 1 quantity squared minus 1 equals negative 2 over 1 plus, last time we did this, I think the number was 1, equals negative 2 over 2, which is negative 1. As x approaches 1, y approaches negative 1 for this strange looking function. Number 13, find the right-hand limit. This is right-hand limit as x approaches 2 from the right side of this this guy right here. Again, substitute 2 into there and say what it should have been getting close to, assuming we can find a value there. So minus 1 equals square root of 4 minus 1 equals square root of 3. And really, look, that's it. Look, this graph, I don't know exactly what it looks like. Probably something like this again, right? When x is, I think here's 1/2. So here's 1 and 1.5 and 2. Here's 2. It's going up to square root of 3 right there. And from the right side, it's approaching the square root of 3. There's no domain restriction here. There's no issues of left and right hand limit or indeterminate of anything else. If something, look, for all these problems, even the ones that got 0 over 0, I tried to substitute the number first to see if I had an issue. Here I didn't have an issue, and right-hand limit says I'm approaching root 3 as I come from the right side. And guess what? I'm approaching root 3 as I come from the left side as well. But they asked for a right-hand limit here, and it's given. There you go. Number 14, use the definition of a derivative to calculate the derivative of f of x equals x squared plus x. So it looks a little bit like the last one that we did here. We're going to use the limit process again. The limit as h approaches 0 of f of x plus h minus f of x all over h. Anywhere you see an x, substitute x plus h in for the function right here. So the derivative will equal the limit as h approaches 0 of, we'll do x plus h quantity squared plus x plus h minus the original function x squared plus x. Notice how I group it in parentheses to make sure I subtract the, the entire thing. All over, let's do it straight. All over, not bad, h. Trust me, it's harder than it looks to do this. Equals limit as h approaches 0 of, this becomes x squared plus 2xh plus h squared plus x plus h minus x squared minus x. Distribute the negative all over h. X squared minus x squared cancels. See, ideally when you do this, all that will exist are terms that only have h in it, even if h has ended up canceling, which they can't. They won't in this case. So we have 2xh plus h, limit. 2xh plus h squared plus h, all divided by h here. Common factor of h exists in every term here. Let's factor it out. That's h times 2x plus h plus 1, all divided by h. Common multiple of h cancels on top and bottom here. Now we can substitute 0 in for h, now that we are no longer dividing by 0 in that case. 2x plus 0 plus 1 is 2x plus 1. So the derivative function is 2x plus 1 for y equals x squared plus x. 2x plus 1, and that is correct there. And again, this determines the slope of the tangent line for this function. Let me do something with you here. I'm going to jump onto Desmos and show you what it is that we actually found so you can make sense of it. I have an old graph here. It is function derivative graph, this one right here. Okay, so what I have here is this nice useful Desmos toolkit where I can plug in my original function, x squared plus x right here. Try my derivative function that I found, which is 2x plus 1. And what I'm going to create here, given all this other junk right here, is a slider for my x value, meaning I can plug in anything for x. And then it's not the y value that I get out per se for this, but it's the y value for this here. When I plug in a number for x like 0, the y value is 0 as well. So at the point 0, 0, we can find the slope of the tangent line to this curve. And you can see the slope is not 0 here. It's actually, it looks like it's 1 over 1. How come? 2 times 0 plus 1 is 1. So your f prime of x, this g of x right here is also f prime of x. Okay, f prime of x below. The slope is 1 tangent to that line. No matter where I slide this thing, I will find the slope of the tangent line to the curve. Now, the slope can be determined in here. If I plug in negative 0.5, 2 times negative 0.5 is negative 1, plus 1 is 0. The slope of the tangent line here is 0. You can do this for all points and all values that are defined on this function here, so for all real numbers. Obviously, you plug in something like 3. 2 times 3 is 6, plus 1 is 7. The slope of this line, this tangent to the point when x is 3, is 7. Okay? 312 is the point on the graph. The slope of the line is 7 that's tangent to it. And you can zoom out and do that forever. Obviously, it'll start to look very vertical if you do it more and more and more. So that little toolkit does help with that, and it helps explain what you found there. Could have done it for the other problem. I'm going to go ahead and, well, actually here, let me look back at the previous problem and see what we had there. The derivative one, it was this one right here, negative x squared plus 2, and the derivative was negative 2x. So let's, not the calculator. Let's try Desmos. Negative x squared plus 2, I think it was, and negative 2x right here. If we want this to be tangent correctly, I can move the slider, and this should run tangentially. If it doesn't, there's something wrong. If it does, there's something right, which is good. Looks like this is sliding appropriately as well. Slope of the tangent line can be determined by plugging it into your derivative function. 0 at 0, that makes sense. All right, getting rid of that. Leave. Okay, let's go and move on. We just did number 14. Number 15. We will find the limit as x increases without bound of this guy right here. Like I did last time, what I'm going to do is kind of just substitute infinity into this, but what I want you to also see here is point of relevance. What if we did plug in infinity straight up? Hang on, infinity minus 5 over infinity squared plus 1. Okay, first of all, concepts of infinity are rather abstract. There's an order of dominance based on the complexity, second power, first power, fraction, etc. One thing I know for sure is infinity minus 5 might as well be infinity. Subtracting 5 or 5 gazillion is nothing like taking a number that's infinitely times larger than that. I can ignore that because it is irrelevant to the case that I'm making here. Same thing with infinity squared plus 1, irrelevant. You might as well treat this like some number divided by itself squared. Like, what if I asked you what x over x squared could simplify to? Well, that's x over x times x, which these can cancel, so it's 1 over x. Same thing here. This degree is 2, which is larger than the degree here that's 1, so this might as well be treated and rewritten as 1 over infinity. This might as well be that, because no matter how large this number is, that larger squared is much more dominant. Much more dominant. So same with 2 times infinity here. 2 times infinity might as well be infinity. So what we're looking at really is 1 plus infinity divided by 1 plus infinity. Excuse me, 1 over infinity plus, I can't speak, 1 over infinity plus 1 over infinity. So that's like 0 plus 0, which is like 0. Okay. That's what this thing's approaching. You can check it with your own graph. Go on Desmos, TI, whatever it is. You'll get that. Last problem, number 16. Approximate using 4 intervals the area of the region between the graph of the function and the x-axis over the specified interval f of x equals 25 minus x squared. Okay, I'm going to first draw this graph, and then I'll explain what it is we're doing. So f of x equals 25 minus x squared. I can also rewrite that as negative 1x squared plus 25, so I can just kind of see where we're at here. What I'm going to do is kind of change the scaling of this graph here to resemble something of significance to me, because I want to get up to 25 here. Let's see, 2, 3, 4. Okay, I couldn't really fit it that way. I'll just do this. 5, 10, 15, 20, 25. I don't know. Is that too small? That's fine. We'll leave it like that. No, I'll go taller. The only problem with going taller here, if I jump every 2, and that means this is 2.5. 2.5, 7.5, and 10. I'll work with it. We might even need to use these numbers. We'll see. 12.5, 15, 17.5, 20, 22.5, and up here would be 25. That's my y-intercept, which is also my vertex. And then over here, I can also stretch this one out a little more as well. How many points would I get for 1, 2, 3, 4, 5? Kind of same thing. Let's make this 1, 2, 3, 4, and 5. Let's make this rather large so you can see a whole bunch of stuff here. So starting at, and remember, these scales are different as far as what we have here, but starting at 0, 25, which is a point on the graph, go over 1, down 1. Now, over 1 is like this. Down 1 is kind of like this here based on the graph. It's just at 24, right? Over 2, down 4, so it's like 21, which is probably around right there. Over 3, down 9, so it's like 16, which is about like right there-ish probably. Over 4, it's probably higher, but that's okay. Over 4, down 16, so it's like 9, like there. And over 5, down 25, so over here. So the graph that we can see is right here. We can use the graphing calculator, of course, as well, but I'm going to get this drawn and worked out a little bit. So here's the curve, okay? What we're going to find, we're going to approximate the area of the region from 0 to 5. And the region is also bounded by x that is greater than 0. We're looking at this shaded region about right here. Okay, now we're going to approximate it. We won't find the exact value. I'll tell you what the exact value is in a moment after we finish this. And for comparison's sake, we'll see if this gets kind of close enough to an answer that we want. And again, I will be using the graphing calculator to kind of work some of this stuff out as well. Okay, so 4 intervals means we're going to create 4 rectangles here. I'll do 2 different sets. I'm going to do rectangles using what's called left endpoint approximation, meaning first let's splice this thing up into 4 rectangles of width 1.25, 1 1/4. We'll start here. We'll go 1 1/4 here. Another 1 1/4 from that is let's see, half, 1 1/4 here. Another 1 1/4 is here. And finally, we end at 5 right here. Here are 4 rectangles where I'm going to make them in purple, right? Or those are the splicings. I'm going to make 4 rectangles here from left endpoints like f of 0, that's 25. F of 1.25, that's this number here. We'll get that in a bit. F of 2.5 and f of 3.75 right there. We're going to find out what the area of these 4 rectangles are. We know their width. We need to know all of their heights. So this is where I'm going to have the calculator help me a little bit. To find the left endpoint approximation area, what I'm going to do is base times height of each rectangle. Now, each rectangle has a width of 1.25. So instead of doing 1.25 times this plus 1.25 times that plus 1.25, I can factor out a 1.25 of each of them, and all that will be left are the heights, whatever f of 0 is, whatever f of 1.25 is, whatever f of 2.5 is, and whatever f of 3.75 is. All those y values that we get are the heights of these 4 rectangles. I'll be adding those things together. Now I'm going to use the calculator to help myself out. What I'm going to do in the calculator is I'm going to go into y equals, create this equation, 25 minus x squared. Okay. And then I'm going to go to my table, and I'm going to plug in the values that I want to plug in. Now, these all are increments of 1.25, so I can just do that. I can start at 0, and I can increase by 1.25 each time. So all 4 of these values, I can find the y values for and go ahead and write them down. Whoops, that's the graph. But the table will give me what I'm looking for here, which are these numbers right here. And I'm going to write them exactly as is and use them. F of 0 is 25. F of 1.25 is this number, then that number. So I think the other one was that 0.75. So I'll try and remember that here. So we have here 1.25 times f of 0, which is 25, plus f of 1, which is 23.4375, plus f of 2.5, which is 18.75, plus f of 3.75, which is 10.9375, I believe. And we'll add those things up, and we'll get an area of these 4 rectangles. Okay, and then I'll talk to you about what we can do based on that. This is, again, left endpoint approximation. So let's go ahead and compute those up. We'll do 25 plus 23.4375, missing a 7, plus 18 point, I can't type on a calculator, 18.75 plus 10.9375. These 4 numbers I'm going to multiply by 1.25 right here. So I'm going to get this number right here. So what I just got, hang on, got some coughs. What I just got is the left endpoint approximation of this area under this curve. And this is square units here. This is left endpoint approximation. I found the area of these 4 rectangles. Now notice, the area of these 4 rectangles is more than the area of the total thing. In fact, this was an overshot of it. So what I'm also going to do beyond just these rectangles right here is I'm also going to do what's called right endpoint approximation. Left endpoint approximation created rectangles from the left endpoints here, 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 and here. Now I'm going to do right endpoint approximation, which creates rectangles from, let's use like red, I think that'll be good, from here here, here, and here. And this is considered, and this one goes down to 0 right there. So that area is going to be 0. And this is considered to be an undershot. The area of these 4 rectangles is significantly less than green. What we end up getting as a result is if we add these ones together, we get that area. We can average these two. And the average of these two will give us kind of these trapezoidal sections. Like imagine if I had a rectangle where this blue line represents the top of this trapezoid and they still have the same height. It would give me this area, the area of this here, plus the area of this here, plus the area of this here, plus the area of this here, which looks a lot closer to our thing. It's a little bit of an undershot, and I'll give you the exact one later. But let's first do right endpoint approximation and figure out what that one's going to be based on what we have here. So for right endpoint approximation, REA, what we're going to do is same thing, same widths. It's going to be 1.25 widths. And now we're not going to do f of 0. We'll do f of 1.25 plus f of 2.5 plus f of 3.75. And the rightmost endpoint here is f of 5. Now, f of 5 we already know to be 0. We already know f of 5 is 0. So what I'm going to do here is, look, we already know these numbers here. F of 1.25 was 23.475. F of 2.5 is 18.75. F of 3.75 is 10.9375. And f of 5 is just 0. That height is 0, so base times height there will be 0 as well. So I'm going to go ahead and do those ones, add those 23.475. Oh, 4375. Whoops, I have something wrong here. 23.4375 plus 18.75 plus 10.9375. That equals this number, 53.125, which is criminally lower than 78.125 was. So this one here is going to be 1.25 times 53.125, which is exactly 66.40625. 66.40625 square units. That's a right endpoint approximation. Now what I'm going to do is average these two numbers here. I'm going to average this one with this one. That'll give me the best approximation of what it is we got there. So this thing will become, we're going to do 97, and a bell's going to ring here for me in a moment. I'm going to talk through that bell if I still have to. It's supposed to be around 50 after, I think. So let's average these two, add them up, divide by 2. So this will be the previous answer here of that plus 97.65625. Add those up. Let's divide those by 2. And my approximate area for that thing, which is just undershot here, is going to be 82.03. So around, I'll say around 82 square units. That's the approximate area under the curve of this shaded region right here. Okay. Now, if you want to get an exact answer, I'll tell you what that is here in a second. Okay. You're not expected to get exact area. You might not even know what it is that I'm going to be doing right here. I just want to get it for you, so you do have something to work off of here. It's 25 minus x squared dx equals. Sorry, I'm going to do something here in the very end. Okay, so we'll get 25 times 5 minus 1/3, 5 cubed, minus 0 squared, 25 times 0, minus 1/3 times 0. Okay, so what we're going to do is we're going to do 25 times 5, that's 125. Let's do minus 1/3 of 5 cubed, that's minus 1/3 of 125. So 1/3 of 125, I don't even know, 40 point something, 40 something. Divided by 3, it's going to be 41 point whatever. Let's do 125 minus that number, and that's going to be a little more than our 82 answer. It'll be about 83 1/3. So the exact answer is 83.3 repeating square units. So that's the exact area there. We got close. We got around 82. And like I said, it would just be undershot because these blue lines are just a little bit less than the green there. Okay, I am done. This is all of it. Hope it was good. I'll be probably here on bell ring, but awesome job, y'all. Thanks for sticking in with me. I'm out. Fiend!